Welcome back. Tonight, we settle in with the gentle, unhurried journey of two spacecraft that left Earth in 1977 and have been drifting ever since through the cold, quiet darkness, carrying with them golden records etched with the sounds of our world, whale songs and thunder and a child's laughter, all traveling at 11 miles per second towards stars they will not reach for 40,000 years. Their radio signals growing fainter now, like whispers across an unimaginable distance. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. In the summer of 1965, a young aerospace engineer named Gary Flandreau was working at the Jet Propulsion Laboratory in Pasadena, California, assigned to a rather theoretical task that would, in time, reshape humanity's understanding of the outer solar system. Flandreau had been asked to study the possibility of using the gravity of one planet to propel a spacecraft toward another, a technique that had been discussed in academic circles but never seriously applied to mission planning on a grand scale. He spent his days with charts and tables and orbital calculations, tracing the slow paths of Jupiter, Saturn, Uranus, and Neptune as they moved through their long years around the Sun. And what he discovered during those quiet months of computation was something quite remarkable, though he likely did not fully appreciate at the time just how consequential his findings would become. What Flandreau found, through patient work with his calculations, was that in the late 1970s, the four giant planets of the outer solar system would arrange themselves in a configuration that occurs only once every 176 years. This alignment, if one can call it that, was not a perfect straight line, but rather a gentle spiraling arc that would allow a spacecraft launched from Earth to visit each of these distant worlds in turn, using the gravity of each planet to bend its trajectory and accelerate it toward the next. The geometry of the solar system, which usually presents such vast distances as to make multi-planet missions impractical, would briefly cooperate in a way that it had not done since the presidency of Thomas Jefferson, and would not do again until the 22nd century. It was, in the language of orbital mechanics, a rare window of opportunity, and Flandreau documented it carefully in his reports to the laboratory. The implications of this discovery were understood gradually, as such things often are in large institutions. If a spacecraft could be launched in 1977, give or take a year, it could theoretically visit all four giant planets in a single mission lasting about 12 years, rather than the 30 or 40 years that would be required if each planet had to be reached independently. The fuel savings alone were extraordinary, as the gravity assists from each planet would provide most of the energy needed to reach the next, reducing the burden on the spacecraft's own propulsion systems to almost nothing. This concept came to be known informally as the Grand Tour, and it captured the imagination of scientists and engineers at the Jet Propulsion Laboratory, who began to develop proposals for a mission that would take advantage of this fleeting celestial arrangement. The original Grand Tour mission, as it was formally proposed in the late 1960s, was an ambitious undertaking that called for 4 sophisticated spacecraft, 2 to visit Jupiter, Saturn, and Pluto, and 2 to visit Jupiter, Uranus, and Neptune. These spacecraft would be equipped with advanced technologies, including autonomous navigation systems and long-lived power sources, and they would carry comprehensive suites of scientific instruments designed to study each planet and its moons in unprecedented detail. The projected cost of this program was substantial, on the order of several $billions, and the technical challenges were considerable, as no spacecraft had ever been designed to operate reliably for the decade or more that such a mission would require. Nevertheless, the scientific community was enthusiastic, and formal studies proceeded through the early 1970s with the expectation that funding would eventually be secured. It was not to be, at least not in that form. The early 1970s were a difficult time for ambitious space programs, as the national priorities that had driven the Apollo missions were shifting, and economic pressures were mounting. The Vietnam War continued to consume vast resources, and a recession was beginning to take hold, and the political appetite for expensive scientific ventures had diminished considerably since the triumphant days of the moon landings. In 1971, the Grand Tour program was formally cancelled by the Nixon administration, a casualty of budget constraints and competing priorities, and it seemed for a time that the rare alignment Flandreau had discovered might pass unexploited, the next opportunity 2 centuries away, long after everyone involved would be gone. But the engineers and scientists at the Jet Propulsion Laboratory were not easily discouraged, and they began almost immediately to develop an alternative proposal, one that might accomplish at least some of the Grand Tour's objectives at a fraction of the cost. This scaled-down concept, which eventually became the Voyager program, called for 2 spacecraft rather than 4, with a primary mission focused on Jupiter and Saturn rather than all 4 giant planets. The spacecraft would be simpler and less expensive than those envisioned for the Grand Tour, though still highly capable, and the mission duration would be reduced from 12 years to approximately 5. It was a compromise, certainly, but it preserved the essential opportunity to explore the outer solar system during the brief window that nature had provided, and it was priced at a level that Congress might conceivably be willing to fund. In 1972, the Voyager program was formally approved, with the Jet Propulsion Laboratory selected as the lead institution for the mission's development. This choice was natural enough, as the laboratory had accumulated decades of experience with planetary exploration, having managed the Mariner missions to Venus and Mars, and its engineers understood the unique challenges of designing spacecraft that would operate far from Earth, where solar power was inadequate and communication signals took hours to arrive. The laboratory, situated in the foothills above Pasadena, became the center of an intense 4-year effort to design, build, and test 2 spacecraft that would carry humanity's instruments to the giant planets, and the work began in earnest with a sense of quiet urgency that reflected the immovable deadline imposed by orbital mechanics. The decision to build 2 identical spacecraft, rather than a single more capable vehicle, reflected a philosophy of redundancy that was central to the mission's planning. Space exploration is an unforgiving endeavor, where a single component failure can end a mission entirely, and by flying 2 spacecraft, the program could tolerate the loss of one while still achieving its primary objectives. This approach also allowed for a certain division of labor, with each spacecraft assigned a slightly different trajectory and set of priorities, so that together they could accomplish more than either could alone. The total budget for both spacecraft, including their launches and the years of operations that would follow, was set at $865 million, a sum that seems modest by later standards, but that required careful stewardship and constant justification during a period of economic difficulty. The compressed development timeline, spanning only 4 years from formal approval to the first launch in 1977, created considerable pressure on the engineering teams. Spacecraft of this complexity typically required longer development periods, with ample time for testing and refinement, but the alignment that Flandreau had discovered would not wait for human convenience, and the launch windows were fixed by the geometry of the solar system. If the spacecraft were not ready by the summer of 1977, the opportunity would begin to degrade, and the extended trajectories to Uranus and Neptune would become impractical. This deadline focused the minds of everyone involved, and the work proceeded with a disciplined intensity that left little room for delay or indecision. The budget battles with Congress were a recurring feature of those years, as the Voyager program had to compete for funding with other national priorities during a period of recession and fiscal restraint. The arguments in favor of the mission emphasized not only its scientific value but also its cost-effectiveness, noting that the rare planetary alignment made it possible to accomplish in a single decade what would otherwise require multiple missions spread across half a century. The engineers and scientists who testified before congressional committees spoke carefully about the modest scope of the program, its reliance on proven technologies wherever possible, and its potential to yield discoveries of lasting importance for a relatively small investment. These arguments were ultimately successful, though the funding remained tight throughout the development period, and compromises were sometimes necessary. Among the key figures who guided the program through these challenging years was John Cassini, who served as the original project manager at the Jet Propulsion Laboratory. Cassini was an experienced engineer who understood both the technical demands of spacecraft development and the institutional complexities of managing a large program within a government bureaucracy. He assembled a team of talented engineers and imposed a discipline on the project that kept it on schedule despite the pressures of the compressed timeline. His role was to make decisions, often under uncertainty, and to keep the various elements of the program moving forward in coordination. And he did this with a steady competence that inspired confidence among his colleagues. Ed Stone, a physicist from the California Institute of Technology, was appointed as the chief scientist for the Voyager mission in 1972, a role he would continue to hold for more than 4 decades. Stone's responsibility was to coordinate the scientific investigations that the spacecraft would carry out, working with the principal investigators of the various instruments to ensure that the mission's objectives were well defined and achievable. He served as a bridge between the engineering teams, who were focused on building spacecraft that would survive the harsh environment of deep space, and the scientific teams, who were focused on understanding the mysteries of the planets and moons that the spacecraft would encounter. His calm and thoughtful approach to this complex task earned him the respect of both communities, and he became the public voice of the mission, explaining its discoveries to the world in terms that were clear and accessible. The twin spacecraft that emerged from this process were identical in their fundamental design, each built around a 10-sided aluminum frame that housed the electronic systems and supported the various instruments and appendages. A large dish antenna, 12 feet in diameter, would serve as the primary means of communication with Earth, transmitting data across the vast distances of the outer solar system at a modest rate that required patience and careful planning. 3 radioisotope thermoelectric generators, containing plutonium dioxide, would provide electrical power where the sun's light was too faint for solar panels, and these generators were designed to produce a steady output for many years, though their power would gradually decline as the plutonium decayed. Each spacecraft carried 11 scientific instruments, selected through a competitive process, and these instruments were designed to study the planets and their moons across a wide range of wavelengths and phenomena, from visible light images to magnetic field measurements to the charged particles of the solar wind. The engineers who designed these spacecraft specified them for a primary mission lasting approximately 5 years, which would be sufficient to reach Saturn and complete the planned observations. This was the formal requirement, the baseline against which the design was validated and the budget was justified. But there was also an informal understanding, never quite stated in official documents but widely shared among those who worked on the program, that the spacecraft might last considerably longer if fortune favored them. The components were selected for reliability, the software was designed for flexibility, and the systems were tested with care that went somewhat beyond what a 5-year mission strictly required. If everything worked as hoped, and if the funding continued, and if the spacecraft remained healthy, there was a possibility, perhaps even a likelihood, that the mission could be extended to take advantage of the trajectories that led beyond Saturn to the more distant worlds. This quiet optimism, held in reserve during the budget debates and congressional hearings, reflected a sensibility that was common among the engineers of that era. They built things to last, when they could, knowing that the most valuable missions often exceeded their original expectations, and that the true measure of their work would not be known for many years. The alignment that Gary Flandreau had discovered was a gift from celestial mechanics, an accident of timing that would not recur for nearly 2 centuries, and those who understood its significance were determined to make the most of it. The spacecraft they were building would carry instruments designed by scientists, images intended for the public, and, as later sections will describe, a record of sounds and greetings intended for any intelligence that might one day find them drifting among the stars. But all of that depended first on the careful, patient work of engineering, on solving the countless small problems that stood between a concept and a functioning spacecraft, and on delivering 2 identical machines to the launch pads in Florida before the summer of 1977 arrived and the window began to close. In the early months of 1976, as the twin Voyager spacecraft were taking shape in the careful hands of engineers at the Jet Propulsion Laboratory in Pasadena, California, a question arose that had nothing to do with thrusters or trajectory calculations, nothing to do with the delicate calibrations of scientific instruments or the precise folding of antenna arrays. The question was softer, more philosophical, and in its own quiet way rather profound. If these spacecraft were destined to journey beyond the outer planets and eventually drift into the vast darkness between the stars, perhaps for millions or even billions of years, ought they not carry some message from the world that had created them, some small testament to the existence of life on a pale blue planet circling an unremarkable yellow star in an outer arm of the Milky Way galaxy? The idea was not entirely new, for the Pioneer spacecraft launched earlier in the decade had carried small plaques bearing simple illustrations of human beings and diagrams indicating Earth's location in the cosmos. But the Voyager missions presented an opportunity for something more ambitious, something richer and more representative of the full breadth of human experience. And so NASA turned to a man whose name had become synonymous with the poetic communication of scientific ideas, a Cornell University astronomer named Carl Sagan, who had helped design the Pioneer plaques and who possessed an unusual gift for contemplating humanity's place in the universe with both scientific rigor and genuine wonder. Carl Sagan accepted the invitation to lead a small committee tasked with creating what would come to be known as the Golden Record, a phonograph record made of gold-plated copper that would accompany each Voyager spacecraft on its journey to the stars. The committee's mandate was extraordinary when one pauses to consider it, for they were asked to assemble a kind of cosmic message in a bottle, a portrait of Earth and its inhabitants intended not for any human audience but for whatever intelligence might one day, perhaps millions of years hence, encounter the drifting spacecraft in the depths of interstellar space. The challenge was immense, the responsibility profound, and the timeline was, to put it gently, rather constrained. NASA granted the committee approximately 6 weeks to compile this message to the cosmos, 6 weeks to decide what sounds and images and greetings might best represent an entire planet, 6 weeks to capture something of the essence of human civilization and the natural world that had given rise to it. This was not a great deal of time when one considers the magnitude of the task, for how does one choose what to include when the audience is unknown, when the recipients might be so utterly different from ourselves that our most basic assumptions about perception and understanding might not apply at all? Nevertheless, the committee set to work with quiet determination, gathering in the comfortable informality of Sagan's home to debate and discuss and gradually assemble the contents of what would become humanity's most far-traveled artifact. Among those who joined this small gathering of minds was a young creative director named Andrew Yang, who had been brought onto the project to help curate the musical selections that would form such an important part of the record. Andrew Yang was a writer with a deep interest in science and an equally deep appreciation for the arts, and she approached the task with both intellectual seriousness and genuine emotional engagement. The work was intense and consuming, requiring long hours of listening and discussing and weighing the merits of one piece of music against another, of one image against the next, of one approach to representing humanity against all the alternatives that might have been chosen instead. As the weeks passed and the work progressed, something unexpected and rather lovely occurred between Carl Sagan and Andrew Yang, for in the midst of compiling a message about the nature of human existence, they found themselves falling deeply in love with one another. The irony was not lost on them, that while searching for ways to communicate the experience of being human to unknown beings in some distant future, they were themselves discovering one of the most profound of all human experiences, the sudden and overwhelming recognition of connection with another person. Their relationship would eventually lead to marriage and a creative partnership that would span decades and produce some of the most beloved science communication of the 20th century. But in those early weeks of work on the Golden Record, it was still new and private and quietly extraordinary. It was during this period of intense work and intense feeling that Andrew Yang participated in an unusual recording session at Bellevue Hospital in New York City. On the 1st of June, 1977, she was connected to an electroencephalograph and other medical equipment designed to capture the electrical activity of her brain and the rhythmic beating of her heart. For approximately 1 hour, she sat quietly while the machines recorded these signals, converting the subtle electrical patterns of her body into audio frequencies that could be pressed into the grooves of the Golden Record. During this session, Andrew Yang meditated on a prepared mental itinerary, moving through thoughts of human history and civilization, through reflections on the conflicts and kindnesses that have marked our species, and through contemplation of what it might mean to be alive on this particular planet at this particular moment in cosmic time. But she also allowed her mind to dwell on more personal matters, on the still new and somewhat overwhelming experience of having fallen in love with Carl Sagan just days before. And so somewhere in the electronic whisper of that recording, compressed into audio frequencies that the human ear cannot meaningfully interpret, but that exist nonetheless as patterns in the analog grooves of the Golden Record, there may be some faint trace of that emotion, some echo of love encoded alongside the other sounds of Earth. It is a quietly romantic notion that a declaration of human affection might be traveling through the darkness of interstellar space even now, carried by spacecraft moving at thousands of kilometers per hour away from the sun that warmed the face of the woman who felt it. The Golden Record contains 115 images encoded in analog form, a technique that stores picture information as audio signals that can theoretically be reconstructed by a sufficiently sophisticated recipient into visual representations of their original subjects. These images were selected to provide a kind of visual introduction to Earth and its inhabitants, beginning with basic scientific information, with diagrams showing mathematical relationships and the structure of our solar system, then progressing gradually toward more particular representations of our planet and its life forms. There are images of continents and oceans, of mountains and deserts and forests, of the intricate structures of cells and the delicate symmetry of snowflakes. There are photographs of animals, from insects to elephants, from fish swimming in clear water to birds in flight against open sky. And there are images of human beings, engaged in the ordinary activities of human life, eating and drinking and working and playing, caring for children and caring for one another. The selection of these images generated some controversy, as such selections invariably do, for among the photographs originally proposed for inclusion were images of nude human beings, anatomical representations intended to convey to unknown recipients some sense of what our species actually looks like beneath the clothing we have adopted for modesty and protection. These images were ultimately excluded from the final selection, a decision that reflected the sensibilities of the era and the nervousness of some officials about potential criticism from certain segments of the public. It is perhaps a small irony that a message intended for beings who might be utterly different from ourselves was shaped in part by concerns about the reactions of our fellow humans here on Earth. The musical selections on the Golden Record represent an attempt to capture something of the extraordinary diversity and emotional range of human musical expression, from the mathematical precision of Johann Sebastian Bach to the passionate intensity of Ludwig van Beethoven, from the traditional music of cultures around the world to the more recent innovations of Western popular music. Bach is represented by several pieces, including the Brandenburg Concerto No. 2 and selections from the Well-Tempered Clavier, their intricate patterns of counterpoint offering a glimpse into a particular kind of human thinking, a way of organizing sound that is both logical and beautiful. Beethoven's Fifth Symphony and his String Quartet No. 13 appear on the record, their emotional depth and structural sophistication representing another facet of human musical achievement. But the committee was careful to include music from beyond the Western classical tradition, recognizing that any honest portrait of human musical expression must acknowledge the contributions of many cultures. There is music from Japan and China, from India and the Middle East, from Africa and the Pacific Islands, each selection carrying its own history and its own way of understanding rhythm and melody and the relationship between sound and feeling. And there is, somewhat famously, a recording of Chuck Berry performing Johnny B. Good, a piece of American rock and roll that generated some debate among committee members about whether such relatively recent popular music belonged alongside the more established masterworks of the classical tradition. In the end, it was included, a recognition that the energy and joy of rock and roll is as authentically human as the sublime architecture of a Bach fugue. Perhaps most haunting among the musical selections is a recording called Dark Was the Night, Cold Was the Ground, performed by a blind American musician named Blind Willie Johnson. This piece, recorded in 1927, features Johnson's guitar and his wordless vocal moaning, a sound that seems to emerge from some deep well of human sorrow and longing. There are no lyrics, only the voice and the instrument together creating something that transcends language entirely, and it is perhaps for this reason that the piece was deemed especially appropriate for inclusion on a record intended for beings who would not understand English or any other human language. The record carries spoken greetings in 55 different human languages, each recording lasting only a few seconds, brief salutations from speakers of Akkadian and Mandarin Chinese, of Russian and Swahili, of Welsh and Zulu and dozens of others. These greetings are simple and friendly, most of them some variation of hello and peace to you and we are thinking of you from across the vastness of space. There is also a message from the President of the United States at the time, Jimmy Carter, whose words express hope that the future might bring greater understanding among all beings, a sentiment that seems both humble and hopeful when one considers the infinite darkness into which it was sent. The golden record is protected by an aluminum cover that serves both as shield and as instruction manual, for engraved upon its surface are diagrams intended to communicate to unknown recipients how the record might be played and interpreted. These pictorial instructions, designed primarily by the astronomer Frank Drake, show the correct speed of rotation, the correct position of the stylus, and the method by which the analog audio signals might be converted back into images. The cover also bears a pulsar map, a diagram showing the position of Earth relative to 14 pulsars, those rapidly rotating neutron stars whose regular radio emissions serve as cosmic lighthouses. The precise frequencies of these pulsars are encoded in binary notation, and because pulsar frequencies change slowly but predictably over time, a sufficiently advanced civilization might theoretically use this map to determine not only where the record came from but approximately when it was created. A stylus is included with each record, a small cartridge mounted in the protective cover, for it was recognized that whatever beings might encounter the Voyager spacecraft would likely not possess phonograph technology of their own. This small needle, carefully secured for its journey through interstellar space, represents a kind of key to the contents within, though of course the recipients would first need to understand the pictorial instructions on the cover and possess the technical capability to construct a playback device from the information provided. It is an optimistic assumption that beings sufficiently advanced to intercept a spacecraft traveling between the stars would also possess the curiosity and capability to decode and play an unfamiliar artifact, but optimism seemed appropriate for such a project. And so the golden records were completed in their 6 short weeks. These small gold-plated discs carrying sounds and images and greetings from a world that would grow ever more distant with each passing moment. They were attached to their respective spacecraft and launched in the late summer of 1977, and they have been traveling outward ever since, through the darkness and the silence, carrying their cargo of human experience toward an uncertain destination and an audience that may never come. In the warm months of 1977, while much of the world went about its ordinary business, 2 spacecraft were being prepared for a journey that would eventually carry them further from Earth than any human-made object had ever traveled before. The summer air at Cape Canaveral in Florida was thick and humid, as it always is during those months, and the technicians and engineers who worked on the launch pads moved through their careful routines with the steady patience that such work demands. There was, in those final weeks before launch, a quality of quiet anticipation, the kind that settles over a place when something significant is about to happen, though the full significance would not become clear for many years to come. The launch complex designated LC-41 sits on the eastern coast of Florida, where the land meets the Atlantic Ocean and the horizon stretches out in a long, unbroken line of blue. This particular site had been used for various rocket launches throughout the 1960s and 70s, and by the summer of '77 it was well established as one of the primary locations from which humanity sent its machines into the darkness beyond our atmosphere. The salt air from the ocean mixed with the industrial sense of rocket fuel and the warm concrete of the launch structures, creating an atmosphere that those who worked there would remember for the rest of their lives, though at the time it was simply the ordinary smell of their workplace. The first of the 2 spacecraft to leave Earth was, somewhat confusingly, named Voyager 2. This apparent contradiction in naming would later require explanation to curious members of the public, but the reasoning behind it was entirely sensible once understood. The mission planners had determined that although Voyager 2 would launch first, its trajectory through the solar system would be a longer and more leisurely one, while the spacecraft that launched second would travel along a faster path and therefore arrive at the planet Jupiter before its sibling. Since the spacecraft that launched on September the 5th would reach Jupiter first, it was given the name Voyager 1, and the spacecraft that launched on August the 20th was designated Voyager 2, despite being the first to leave the ground. This naming convention prioritized the order of arrival rather than the order of departure, which made perfect sense from a scientific perspective, even if it occasionally caused mild confusion in casual conversation. On the 20th of August, 1977, Voyager 2 sat atop its rocket in the early morning hours, waiting for the moment when the countdown would reach 0 and the engines would ignite. The rocket that would carry it away from Earth was a Titan IA Centaur, a substantial launch vehicle that combined the power of a Titan III first stage with the precision of a Centaur upper stage. This particular combination had proven itself reliable in previous missions, and the engineers had confidence in its ability to send the spacecraft on its way with the necessary velocity and accuracy. The Titan I stood approximately 50 meters tall, a column of metal and fuel and carefully engineered components, all designed for the singular purpose of accelerating the relatively small spacecraft at its tip to the tremendous speeds required to escape Earth's gravitational embrace. When the moment of launch arrived, the engines roared to life with the characteristic thunder of a rocket leaving the ground, and Voyager 2 began its ascent through the Florida sky. For the first several seconds, everything proceeded according to the carefully calculated plan, and the tracking stations monitored the rocket's progress with their usual attentiveness. However, approximately 8 seconds after liftoff, something unexpected occurred. The rocket began to veer from its intended course, deviating in a way that caused considerable concern among those watching from the control rooms. In those few seconds, the possibility of mission failure hung in the air, unspoken but present in the minds of everyone who understood what was happening. The guidance system had encountered some difficulty, and the rocket was not traveling along the path it was supposed to follow. Then, with the kind of quiet competence that characterizes well-designed systems, the rocket corrected itself. The deviation was recognized, compensated for, and the Titan I Centaur returned to its proper trajectory as though the moment of uncertainty had never happened. The entire episode lasted only a few seconds, but for those watching it unfold, those seconds stretched out with the peculiar elasticity that time seems to acquire during moments of tension. In the end, however, the correction was successful, and Voyager 2 continued on its way, passing through the atmosphere and into the darkness beyond. The spacecraft separated from its rocket stages at the appropriate moments, and soon it was traveling freely through space, its nuclear generators providing power and its antenna pointed back toward the distant planet it had just left. 16 days later, on the 5th of September, 1977, Voyager 1 followed its sibling into the sky. This second launch proceeded more smoothly than the first, without the momentary deviation that had caused such brief concern during Voyager 2's departure. The same type of Titan I Centaur rocket carried Voyager 1 away from Launch Complex 41, accelerating it to the velocities necessary for its faster trajectory toward Jupiter. The engineering teams had prepared everything with the same meticulous care they had applied to the first launch, and their efforts were rewarded with a textbook departure that placed the spacecraft precisely where it needed to be. Each of the twin Voyagers weighed 825.5 kilograms at launch, a mass that included all of their scientific instruments, their communication equipment, their structural components, and the fuel they would need for small adjustments to their trajectories in the years to come. This weight had been carefully calculated to balance the scientific capabilities of the spacecraft against the limitations of the launch vehicle and the requirements of the journey. Every kilogram mattered, and the engineers had spent considerable effort determining exactly what equipment to include and how to arrange it most efficiently within the spacecraft structure. The most distinctive feature of each Voyager spacecraft, and the one most often visible in photographs, is the large high-gain antenna dish that dominates its appearance. This dish measures 3.7 meters in diameter, a substantial structure that serves as the primary means by which the spacecraft communicates with Earth. Radio signals traveling across the vast distances of the outer solar system become extremely faint, spreading out and weakening as they cross the millions and eventually billions of kilometers between the spacecraft and the receiving stations on Earth. The large dish helps to focus these signals, both when transmitting messages back to Earth and when receiving commands and instructions from the mission controllers. Without this antenna, the spacecraft would be essentially silent, unable to share the data collected by their instruments or to receive the guidance necessary to carry out their scientific objectives. Power for the Voyager spacecraft comes from 3 radioisotope thermoelectric generators, commonly referred to by their initials as RTGs. These devices represent one of the most reliable means of generating electricity in the cold darkness of the outer solar system, where the sun's light is far too weak to power conventional solar panels effectively. Each RTG contains a quantity of plutonium-238, a radioactive isotope that generates heat as it undergoes natural decay. This heat is then converted into electrical power through the thermoelectric effect, which produces electricity from the temperature difference between the hot interior of the generator and its cooler exterior. The beauty of this approach, from an engineering perspective, is its simplicity and reliability. There are no moving parts to wear out, no complex mechanisms to fail, just the steady and predictable decay of the plutonium-producing heat that is converted into the electricity the spacecraft needs to operate. At the time of launch, the 3 RTGs on each spacecraft generated approximately 470 watts of electrical power, enough to operate all of the scientific instruments and communication equipment simultaneously. Over time, as the plutonium slowly decays and produces less heat, this power output gradually diminishes, but the decline is predictable and the spacecraft systems were designed to operate on decreasing amounts of power over the course of the mission. Even now, decades after launch, the remaining power is sufficient to keep some systems operational, a testament to the thoughtful engineering that went into the original design. Each Voyager spacecraft carries 10 scientific instruments, carefully selected to provide a comprehensive view of the planets and moons they would encounter along their journeys. These instruments include cameras for capturing images in visible light, spectrometers for analyzing the composition of atmospheres and surfaces, magnetometers for measuring magnetic fields, and detectors for studying charged particles and cosmic rays. There are also instruments for measuring the temperatures of planetary surfaces and atmospheres, and for detecting radio emissions from the giant planets and their magnetospheres. Together, these 10 instruments form a remarkably capable scientific payload, compact enough to fit within the mass limitations of the spacecraft, while comprehensive enough to gather data that would transform our understanding of the outer solar system. The arrangement of these instruments on the spacecraft body was the result of careful deliberation, as each instrument had specific requirements for pointing direction, thermal environment, and proximity to other equipment. The cameras and some other instruments are mounted on a movable platform that can be pointed at specific targets, while other instruments are fixed in position on the spacecraft body or at the ends of long booms that extend away from the main structure. These booms serve to separate sensitive instruments from the electrical and magnetic interference produced by the spacecraft itself, allowing for cleaner and more accurate measurements of the surrounding space environment. After leaving Earth, the Voyager spacecraft began the long process of establishing regular communication with the Deep Space Network, the collection of large radio antennas that NASA uses to communicate with spacecraft throughout the solar system and beyond. The Deep Space Network consists of 3 primary facilities, located approximately 120 degrees apart around the Earth so that at least one station can communicate with any distant spacecraft at all times. These facilities are located near Madrid in Spain, near Goldstone in California, and near Canberra in Australia, and together they provide continuous coverage of the sky. The first communication received from the Voyager spacecraft came through the station in Australia, where the large antenna dishes listened for the faint radio signals crossing the growing distance from Earth. The Australian facility, nestled in the quiet landscape near Canberra, played a crucial role in those early days of the mission, as it would continue to do for the decades that followed. The signals from the spacecraft, traveling at the speed of light but weakening with every kilometer of distance, arrived at the dish antennas and were carefully amplified and decoded to reveal the data they carried. This data included information about the health of the spacecraft systems, the readings from the scientific instruments, and eventually the images that would captivate the world when the spacecraft reached their planetary destinations. The process of communication across such vast distances requires patience and precision, qualities that characterize the mission from its earliest days. Commands sent from Earth take time to reach the spacecraft, and the responses take equally long to return, a delay that grows longer as the spacecraft travel further from home. This fundamental constraint shapes every aspect of how the spacecraft are operated, requiring careful planning and the ability to trust the onboard systems to handle situations that arise in between communication sessions. As the summer of 1977 faded into autumn and then winter, the 2 Voyager spacecraft continued their outward journeys, growing smaller in the tracking data as they receded from Earth at speeds that had never before been achieved by spacecraft bound for the outer planets. The successful launches marked the beginning of a mission that would exceed all expectations in its scope and duration, carrying human-built instruments to places that had previously existed only as points of light in telescope eyepieces and fuzzy images in astronomical photographs. The Titan I Centaur rockets had done their job. The spacecraft had survived the violence of launch and the correction of that brief deviation, and the long journey toward Jupiter and beyond had begun in earnest. As Voyager 1 continued its long and patient journey outward through the solar system, the distant point of light that was Jupiter grew steadily larger in the spacecraft's cameras, and what had been merely a bright wandering star in the night skies of Earth began to resolve itself into something far more substantial and far more wondrous than anyone could have fully anticipated. The approach to Jupiter was measured not in the sudden arrival of a traveler at a destination, but rather in the gradual accumulation of detail, the slow revelation of features that had been hidden from human eyes for all the centuries we had gazed upward at this most prominent of planets. And so, in the early months of 1979, as the spacecraft drew closer and closer to the giant world, the scientists and engineers at the Jet Propulsion Laboratory found themselves witnesses to a transformation, as Jupiter ceased to be an object of distant speculation and became instead a place, a world with weather and moons and mysteries that would take many lifetimes to fully comprehend. The closest approach of Voyager 1 to Jupiter occurred on the 5th of March, 1979, when the spacecraft passed within approximately 349,000 kilometers of the planet's swirling cloud tops. This distance, while it may seem considerable by the standards of earthly travel, was remarkably close for a spacecraft moving at such tremendous speed past such an enormously massive world. Jupiter, after all, is a planet of almost incomprehensible scale, a world so large that more than 1,300 Earths could fit within its volume, and its gravitational influence extends outward for millions upon millions of kilometers in every direction. The spacecraft's trajectory had been calculated with extraordinary precision, taking into account not only the gravitational pull of Jupiter itself, but also the subtle influences of its many moons. And as Voyager 1 swept past the planet, its instruments recorded observations that would fundamentally alter our understanding of the outer solar system and everything within it. Among the many discoveries made during the Jupiter encounter, perhaps none was more unexpected or more significant than the observation of active volcanism on the moon Io, which represented the first detection of volcanic activity anywhere beyond the Earth. This discovery came about not during the initial excitement of closest approach, but several days afterward, on the 8th of March, 1979, when a navigation engineer named Linda Morabito was carefully examining images of Io that had been taken to help refine the spacecraft's trajectory. In the course of her work, Morabito noticed a peculiar crescent-shaped feature extending from the limb of the moon, a bright plume rising high above the surface and catching the sunlight in a way that could not be explained by any known geological feature. What she had found was the volcanic plume of a massive eruption, material being ejected hundreds of kilometers above the surface of Io in a continuous fountain of gas and particles. And in that moment of recognition, our understanding of the moons of the outer planets changed forever. Further analysis of the images from Voyager 1, combined with the observations that would later be made by Voyager 2, revealed that Io was home to not one but 9 active volcanoes, making it the most volcanically active body in the entire solar system. The source of this remarkable activity was found to be the intense tidal heating generated by Io's orbital resonance with the other large moons of Jupiter, a gravitational interaction that continuously flexes and deforms the moon's interior and generates enormous amounts of heat. The surface of Io was revealed to be a landscape of extraordinary color and violence, painted in shades of yellow and orange and red by the sulfurous compounds ejected from its many volcanic vents, and entirely devoid of impact craters because the constant volcanic activity resurfaces the moon so rapidly that any craters are quickly buried or erased. This small world, roughly the size of our own moon, had been transformed by the forces acting upon it into something utterly unlike anything that had been observed before. The Jupiter encounter also brought the discovery of a faint ring system encircling the planet, a delicate structure that had escaped detection from Earth despite centuries of telescopic observation. The ring was exceedingly thin and composed of very fine particles that did not reflect sunlight efficiently when viewed from our terrestrial vantage point. But when Voyager 1's cameras captured images looking back toward the Sun with Jupiter silhouetted against the light, the ring material scattered the sunlight forward and became visible as a ghostly band encircling the planet's equator. This discovery demonstrated that ring systems were not unique to Saturn, as had long been assumed, and suggested that such structures might be common features of the giant planets of our solar system and perhaps of planetary systems throughout the galaxy. The moon Europa, though smaller and less obviously dramatic than Io, presented its own set of profound mysteries during the Voyager encounters. The images returned by the spacecraft revealed a surface unlike that of any other world yet observed, a globe of water ice that appeared remarkably smooth on a large scale but was covered with an intricate network of dark lines that crisscrossed the surface in complex patterns resembling nothing so much as the cracks in a frozen lake on Earth. The relative absence of impact craters on Europa's surface suggested that the ice was geologically young and was being continuously renewed or resurfaced by some internal process, and the nature of the cracked terrain strongly implied that the icy shell might be floating atop a layer of liquid water, an ocean hidden beneath the frozen surface. This possibility, that Europa might harbor a vast subsurface ocean of liquid water, would prove to be one of the most tantalizing discoveries of the entire Voyager mission and would shape the direction of planetary exploration for decades to come. Jupiter's Great Red Spot, which had been observed through telescopes since at least the 17th century, was revealed by Voyager's cameras to be an anticyclonic storm of almost unimaginable scale and power. The storm was found to be larger than the entire Earth, a swirling vortex of gas that rotated counterclockwise with winds reaching speeds of approximately 400 miles per hour at its periphery. The images captured during the flyby showed the complex internal structure of the storm, with smaller eddies and cloud features being drawn into its circulation and sheared apart by the differential rotation of the vortex. The persistence of this storm over centuries of observation, combined with the detailed measurements made by Voyager, provided invaluable data about the dynamics of planetary atmospheres and the conditions that allow such enormous weather systems to form and maintain themselves over such extended periods of time. Voyager 2 arrived at Jupiter on the 9th of July, 1979, following a trajectory that had been designed to complement the observations made by its twin spacecraft 4 months earlier. The second encounter provided additional coverage of the planet and its moons, filling in gaps in the observations and allowing scientists to study changes that had occurred in the intervening period. During its approach, Voyager 2 discovered 2 previously unknown moons orbiting close to Jupiter, small irregular bodies that were given the names Thebe and Metis. These tiny moons, each only a few tens of kilometers in diameter, had been hidden from terrestrial observers by their proximity to Jupiter's brilliant glow and their small size. But Voyager's cameras, positioned far closer to the planet, were able to detect them against the darkness of space and add them to the growing census of Jovian satellites. The radiation environment around Jupiter proved to be far more intense and hazardous than had been anticipated, and during the Voyager 1 encounter, the spacecraft's camera platform sustained damage from the bombardment of high-energy particles trapped in Jupiter's powerful magnetic field. Jupiter possesses a magnetic field approximately 20,000 times stronger than that of Earth, and this field traps and accelerates charged particles to tremendous energies, creating radiation belts that posed a significant threat to the delicate electronics aboard the spacecraft. The damage to the camera platform, while not disabling, served as a reminder of the harsh conditions that prevail in the vicinity of Jupiter and informed the planning for subsequent missions to the outer planets, which would need to be designed with greater radiation hardening to survive extended operations in such environments. Ganymede, the largest of Jupiter's moons and indeed the largest moon in the entire solar system, was revealed by Voyager's cameras to be a world of considerable complexity and interest. With a diameter of approximately 5,268 kilometers, Ganymede exceeds even the planet Mercury in size, though its lower density means that its mass is considerably less. The surface of Ganymede was found to display 2 distinct types of terrain: ancient, dark regions heavily cratered by billions of years of impacts, and younger, lighter regions marked by grooves and ridges that suggested some form of tectonic activity in the Moon's past. The presence of these tectonically modified regions indicated that Ganymede had experienced internal heating and geological activity at some point in its history, though the Moon appears to be largely quiescent today. The complex magnetic field of Jupiter was mapped in unprecedented detail by the magnetometers carried aboard both Voyager spacecraft, revealing a structure far more intricate than simple theoretical models had predicted. The field was found to be tilted with respect to Jupiter's rotational axis and offset from the center of the planet, creating a dynamic magnetosphere that wobbles and shifts as the planet rotates. The interaction between this magnetic field and the solar wind, the constant stream of charged particles flowing outward from the Sun, creates a vast magnetospheric bubble extending millions of kilometers in the direction away from the Sun, a region of space dominated by Jupiter's magnetic influence rather than the Sun's. The Voyager measurements provided the foundation for our modern understanding of Jovian magnetospheric physics and the complex plasma processes that occur within it. The small inner moon Amalthea, which orbits closer to Jupiter than any of the large Galilean satellites, was imaged in detail for the first time during the Voyager encounters, revealing it to be an irregularly shaped body quite unlike the spherical forms of the larger moons. Amalthea measures approximately 270 kilometers along its longest axis and is colored a distinctive dark red, the reddest object in the solar system, likely due to the accumulation of sulfurous material ejected from the volcanoes of Io. The irregular shape of Amalthea indicated that it was not large enough for its own gravity to have pulled it into a spherical form, and its battered surface testified to a long history of impacts in the crowded inner regions of the Jovian system. As the two Voyager spacecraft departed the Jupiter system and continued on their respective trajectories towards Saturn and the worlds beyond, they left behind a transformed understanding of the giant planet and its family of moons. The discoveries made during the Jupiter encounters had exceeded all expectations, revealing active volcanism, possible subsurface oceans, delicate ring systems, and a host of other phenomena that had never been imagined before the spacecraft arrived. The data collected during those brief but intensely productive flybys would be studied for years and decades to come, yielding insights and raising questions that would inspire generations of scientists to continue the exploration of the outer solar system. And the spacecraft themselves, having survived the hazards of the Jovian radiation environment and accomplished their primary objectives with remarkable success, were now bound for Saturn, where new wonders and new discoveries awaited them in the cold and distant reaches of our solar neighborhood. On the 12th of November, in the year 1980, the Voyager 1 spacecraft arrived at Saturn, having journeyed through the darkness of space for more than 3 years since leaving Jupiter behind, and the mission controllers at the Jet Propulsion Laboratory, who had spent countless hours planning every detail of this encounter, found themselves at last witnessing the culmination of a trajectory that had been calculated with extraordinary precision, a path through the solar system that would bring the spacecraft closer to Saturn's mysteries than any human-made object had ever ventured before, and the images and data that began to stream back across the vast emptiness between that distant world and our own would change forever our understanding of the ringed planet, revealing secrets that had remained hidden since Galileo first turned his simple telescope toward that curious elongated shape in the sky, so very long ago, in an age when the true nature of those appendages could not even be imagined. The approach to Saturn had been planned with meticulous care over many years, and the engineers and scientists who designed Voyager 1's trajectory had made a decision that would define not only the Saturn encounter but the entire future path of the spacecraft through space and eventually beyond, for they had chosen to send Voyager 1 on a course that would bring it remarkably close to Titan, Saturn's largest moon, a world that had tantalized astronomers for decades with its thick, hazy atmosphere that obscured any view of the surface below, and this deliberate trajectory, which would carry the spacecraft to within 6,490 kilometers of Titan's cloud tops, came with a significant cost, one that the mission planners had weighed carefully against the scientific rewards they hoped to gain, because the gravitational influence of Titan, combined with the specific angle of approach required for the closest possible study of that mysterious moon, would bend Voyager 1's path in such a way that it could no longer continue onward to visit Uranus and Neptune, as its twin Voyager 2 would later do, and instead the spacecraft would be flung upward, out of the flat plane in which most of the planets orbit the Sun, beginning a long climb toward the boundary of the solar system itself. This sacrifice, if one might call it that, was made because Titan represented one of the most compelling targets in all the outer solar system, for here was a moon larger than the planet Mercury, wrapped in an atmosphere so dense and so opaque that no one could say with certainty what lay beneath those orange-brown clouds. And the thick shroud of haze that enveloped Titan had led some scientists to speculate about the presence of organic chemistry, complex carbon-based molecules that might hold clues to the processes that preceded the origin of life on our own world billions of years ago. And so the decision was made to prioritize this close encounter with Titan above all other possible destinations, accepting that Voyager 1's grand tour of the outer planets would end here, at Saturn, while trusting that Voyager 2, following behind, would carry on to explore the more distant ice giants that had never been visited by any spacecraft from Earth. As Voyager 1 swept past Titan at that close distance of just over 6,000 kilometers, its instruments peered through the haze and measured the composition of the atmosphere, and what they found exceeded even the most optimistic expectations of the researchers who had advocated so strongly for this encounter, for the atmosphere proved to be remarkably thick, denser than the atmosphere of Earth itself, extending far above the solid surface and pressing down with a surface pressure roughly 1.5 times that which we experience at sea level on our own planet. And this came as something of a surprise, for no other moon in the solar system possessed anything like this substantial blanket of gases, and Titan suddenly seemed less like the airless rocky and icy bodies that populate most of the outer solar system, and more like a small frozen world with its own weather, its own clouds, its own complex atmospheric chemistry unfolding slowly in the dim sunlight that filters through those distant skies. The composition of Titan's atmosphere, as revealed by Voyager 1's careful measurements, proved to be primarily nitrogen, much like the air we breathe here on Earth, though of course lacking the oxygen that makes our atmosphere suitable for animal life. And mixed with this nitrogen were traces of methane and other hydrocarbon compounds. And the scientists who studied these findings began to realize that methane might play a role on Titan similar to the role that water plays on Earth, existing as a gas in the atmosphere but potentially condensing into clouds and falling as rain, perhaps collecting in lakes and seas on the surface below, though the thick haze prevented any direct observation of what might lie beneath. And this tantalizing possibility of a methane cycle, with rain and rivers and perhaps even oceans of liquid hydrocarbons, would have to wait for future missions to investigate. But the seeds of that understanding were planted here, during those brief hours when Voyager 1 raced past and gathered what data it could before being pulled away by the relentless tug of orbital mechanics. The close approach to Titan accomplished, Voyager 1 continued past Saturn and then, just as the mission planners had known it would, the spacecraft began to climb, its trajectory carrying it upward and away from the ecliptic plane, that imaginary flat disk in which Earth and the other planets trace their orbits around the Sun. And from this point forward Voyager 1 would travel alone through a region of space where no planet waited to be explored, heading instead toward the distant boundary where the influence of our Sun gives way to the interstellar medium, that vast ocean of particles and fields that fills the space between the stars. And this journey continues to this day, the spacecraft still functioning after all these decades, still sending back whispers of data from a distance so great that the radio signals take many hours to reach us. Nearly 10 months after Voyager 1's encounter with Saturn, on the 26th of August in 1981, Voyager 2 arrived at the ringed planet, and because its sister ship had already made the close study of Titan, the mission controllers were free to send Voyager 2 on a different trajectory, one that would allow it to continue onward to Uranus and Neptune in the years to come. And this meant that Voyager 2 could focus its attention on other aspects of the Saturnian system, examining the rings and the other moons from angles and distances that complemented the observations made by Voyager 1. And together the two spacecraft provided a portrait of Saturn that was far richer and more detailed than either could have achieved alone. The rings of Saturn had been known to astronomers for centuries, ever since Christian Huygens correctly interpreted the strange appendages that Galileo had observed. And through earthbound telescopes, these rings appeared to consist of several broad bands separated by gaps, the most prominent being the Cassini division, a dark lane that seemed to divide the ring system into two main parts. But what Voyager 1 and Voyager 2 revealed was something far more intricate and far more beautiful. For the rings were not composed of just a few simple bands, but rather of thousands upon thousands of individual ringlets, each one a delicate strand of ice and rock particles orbiting Saturn in its own narrow track. And the complexity of this structure, visible in the detailed images sent back by the spacecraft cameras, astonished the scientists who had expected something far simpler. And it became clear that the physics governing the rings was more subtle and more interesting than anyone had previously imagined. Among the most puzzling features discovered in the rings were the strange radial markings in the B ring, dark streaks that appeared to extend outward from Saturn like the spokes of a wheel. And these spokes seemed to defy the basic principles of orbital mechanics that Johannes Kepler had established centuries ago. For according to Keplerian physics, particles closer to Saturn should orbit faster than particles farther out, and any radial feature should quickly be sheared apart and stretched into a spiral. Yet these spokes maintained their shape for hours at a time, rotating with the ring as if they were solid structures painted onto a spinning disk. And the explanation for this phenomenon proved to involve electrostatic forces, tiny electrical charges on the ring particles interacting with Saturn's magnetic field, lifting the smallest dust grains above the ring plane and creating these ghostly dark markings that appeared and faded as the spacecraft watched. A reminder that even in the seemingly simple physics of orbiting particles, nature can surprise us with unexpected subtlety. The Voyager spacecraft also discovered something remarkable about how certain features of the rings maintained their sharp edges and narrow shapes, for they found small moons, previously unknown, that orbited on either side of the thin F ring. And these moons, which were given the names Prometheus and Pandora, seemed to act as gravitational shepherds, their gentle tugging on the ring particles preventing them from spreading out and diffusing into space. And this discovery of shepherd moons explained not only the F ring but suggested that similar processes might be at work throughout the ring system, with small embedded moons and moonlets helping to shape and confine the countless ringlets that make up this elaborate structure. And the finding opened up new avenues of research into the complex gravitational interactions that govern the lives of planetary rings. The F ring itself proved to be one of the strangest features in the entire Saturnian system, for rather than appearing as a simple circular band of particles, it showed a peculiar braided structure in some of the images, with what appeared to be 2 or 3 separate strands woven around each other like threads in a rope. And this braided appearance puzzled the scientists who first examined the images, for no one had expected ring particles to behave in this way. And the explanation turned out to involve the gravitational influence of the shepherd moons Prometheus and Pandora, whose orbits are not perfectly circular but slightly elliptical, causing them to periodically approach the ring more closely and then recede. And these regular perturbations create waves and kinks in the ring material that can produce the appearance of intertwined strands when viewed from certain angles. A reminder that appearances can be deceiving and that careful analysis is often required to understand what the cameras reveal. Beyond the rings, the Voyager spacecraft turned their attention to Saturn's many moons, and among these the small icy world called Enceladus proved to be one of the most intriguing, for its surface appeared remarkably bright and smooth in places, reflecting nearly all of the sunlight that fell upon it. And this high reflectivity suggested that the surface was covered with fresh ice, relatively uncontaminated by the dark material that accumulates on older surfaces in the outer solar system. And in some regions the terrain appeared remarkably young, with few impact craters to mark the passage of time. And this youthful appearance hinted at some process of resurfacing, some geological activity that was renewing the face of this small moon, though the nature of this activity would not be fully understood until many years later when the Cassini spacecraft discovered the remarkable geysers of water ice erupting from Enceladus's south polar region. But the Voyager observations had already planted the seed of curiosity that would eventually blossom into one of the most exciting discoveries about habitability in the outer solar system. Another moon that captured attention was Mimas, which displayed on its surface an enormous impact crater, so large in proportion to the moon itself that it seemed remarkable the little world had survived the collision at all. And this crater, named Herschel after the astronomer who discovered Mimas in 1789, spans nearly one-third the diameter of the entire moon and features a towering central peak that rises from its floor. And the overall appearance of Mimas with this massive crater reminded many observers of the fictional Death Star from popular science fiction films that had been released just a few years before Voyager's arrival, a comparison that was made frequently in the press coverage of the encounter. Though of course Mimas is simply a heavily cratered ice moon, its resemblance to any fictional weapon being purely coincidental and arising from the universal physics of impact crater formation. The Voyager encounters with Saturn also resulted in the discovery of 4 previously unknown moons, small bodies orbiting among the rings and in various locations around the planet. And these discoveries added to the growing census of Saturn's satellite family, which would continue to expand in the decades that followed as more powerful telescopes and later spacecraft missions revealed ever smaller and more distant moons. But the Voyagers had demonstrated that the Saturnian system was far more populous and far more complex than earlier generations of astronomers had known, and the data gathered during these brief flybys would be studied for years afterward, each image and each measurement containing information that patient researchers would continue to extract and interpret long after the spacecraft themselves had departed and continued their journeys outward, into the darkness between the stars. After departing the ringed magnificence of Saturn in August of 1981, Voyager 2 began the longest solitary voyage of its remarkable journey, a 5-year crossing of the outer solar system toward a destination that no human-made object had ever approached, and that no human-made object has visited since. The spacecraft traveled onward through the darkness, its instruments quiet and waiting, its antenna pointed always toward the distant blue dot of Earth, while the mission controllers on the ground counted the days and the months and eventually the years until their small ambassador would reach the tilted world of Uranus. This crossing represented the longest gap between planetary encounters of the entire Voyager mission, and during those 5 years the spacecraft drifted farther from the Sun than any active probe had traveled before, passing through regions of space where the solar wind grew thin and the temperature of the surrounding void dropped to levels that tested the very limits of the spacecraft's design. The engineers at the Jet Propulsion Laboratory used this time wisely, sending software updates across the vast distance to improve the spacecraft's capabilities, refining its ability to take long-exposure photographs in the dim light of the outer solar system, and preparing its systems for the unique challenges that awaited at Uranus. On January 24, 1986, Voyager 2 swept past Uranus at a closest approach of approximately 22,000 kilometers, passing near the cloud tops of this strange and tilted giant in an encounter that lasted only a few hours but transformed our understanding of one of the solar system's most peculiar worlds. The spacecraft arrived at Uranus carrying with it 5 years of accumulated distance, 5 years of drifting through the darkness beyond Saturn, and it returned to us images and data that revealed a planet unlike anything we had seen before, a world that had been rolling on its side for billions of years, spinning with its poles pointed nearly at the Sun rather than perpendicular to its orbit as the other planets do. This extreme axial tilt of approximately 98 degrees means that Uranus essentially tumbles around the Sun like a ball rolling along its orbital path, presenting first one pole and then the other to the distant warmth of our star over the course of its 84-year orbit. The cause of this extraordinary orientation remains a matter of gentle speculation among planetary scientists, who suspect that sometime in the distant past, perhaps during the violent early epochs of solar system formation, a large body collided with Uranus and knocked it over onto its side, leaving it to spin in this peculiar fashion for the rest of eternity. When Voyager 2 arrived at Uranus, the southern pole of the planet was pointed almost directly at the Sun, a consequence of the extreme tilt and the particular point in the Uranian year at which the encounter occurred. This meant that the spacecraft approached what might be called the dark side of the planet, the hemisphere that was turned away from the Sun and shrouded in the long winter night that lasts for decades on this distant world. The approaching spacecraft looked upon a dim and shadowed face, illuminated only by the faint reflected light from the sunlit side and the distant stars, and the cameras had to work carefully in the low light to capture images of the cloud tops and the ring system and the collection of moons that orbited in strange and tilted planes around their strange and tilted parent, the sunlit southern hemisphere. When the spacecraft finally swept around to observe it, appeared as a nearly featureless blue-green disk, smooth and calm and curiously unremarkable compared to the banded and stormy faces of Jupiter and Saturn. The atmosphere of Uranus, composed primarily of hydrogen and helium with a small but significant percentage of methane, absorbs the red wavelengths of the faint sunlight that reaches it and reflects back the blue and green, giving the planet its distinctive color, like a pale and distant aquamarine floating in the darkness at the edge of the solar system. The apparent lack of features in the Uranian atmosphere puzzled the scientists who examined the Voyager images, for they had expected to find the kinds of storms and bands and atmospheric patterns that characterize the other giant planets. Instead, Uranus presented a face of remarkable uniformity, a smooth and almost bland expanse of blue-green clouds that revealed few of the dynamic processes occurring in the atmosphere below. This relative quietude may be related to the planet's extreme tilt and the unusual way in which solar energy is deposited into its atmosphere, or it may be connected to the internal heat budget of the planet, which appears to be much lower than that of Jupiter and Saturn, as though Uranus has somehow lost or never possessed the same reservoir of primordial warmth that drives the weather systems of its larger cousins. The temperature readings taken by Voyager 2 revealed an atmosphere chilled to approximately -224 degrees Celsius, making Uranus one of the coldest places in the solar system, a world where the methane clouds drift in perpetual deep freeze and the sluggish atmospheric motions barely disturb the smooth face of the planet. The magnetic field of Uranus proved to be one of the most surprising discoveries of the entire encounter, for it violated nearly every assumption that scientists had made about how planetary magnetic fields should be organized. The magnetic axis of Uranus is tilted by approximately 59 degrees from the planet's rotational axis, and the center of the magnetic field is offset from the center of the planet by roughly 1/3 of the planetary radius. This means that the magnetic field of Uranus is not only tilted at an extreme angle but is also generated by processes occurring somewhere other than the planet's core, perhaps in a conducting layer of water, ammonia, and methane ices that exists deep within the planet's interior. The resulting magnetosphere is twisted and asymmetric, wobbling and tumbling through space as Uranus rotates, creating a complex interaction with the solar wind that differs fundamentally from the more orderly magnetic environments of the inner planets and of Jupiter and Saturn. This discovery forced scientists to reconsider their models of planetary magnetic field generation and open new questions about the internal structure of the ice giant planets that remain topics of quiet investigation to this day. Voyager 2 also revealed the delicate ring system of Uranus in unprecedented detail, discovering 2 new rings to add to the 9 that had been detected from Earth using stellar occultation techniques in the years before the encounter. The rings of Uranus are fundamentally different from the bright and icy rings of Saturn, consisting instead of some of the darkest particles in the solar system, chunks of carbon-rich material that reflect only a tiny fraction of the light that falls upon them. These dark rings are narrow and thin, separated by wide gaps of empty space, and they orbit the tilted planet in the same unusual plane as the moons, circling above what would be the planet's equator if Uranus were not lying on its side. The ring particles are thought to be the remains of moons that were shattered by impacts long ago, or perhaps material that was prevented from coalescing into moons by the gravitational influence of nearby satellites, and they drift in their dark orbits around the blue-green giant, invisible to all but the most sensitive instruments and the brief close approach of a passing spacecraft. The moons of Uranus captured the particular attention of the Voyager science team, for the spacecraft discovered 10 previously unknown satellites during its brief flyby, bringing the total number of known Uranian moons to 15 at the time. These moons orbit in the same tilted plane as the planet's equator and rings, forming a system that is itself tipped on its side relative to the plane of the solar system, and many of them are small and dark and irregular, captured asteroids or fragments of larger bodies that have found their way into orbit around the distant ice giant. The 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, had been discovered from Earth over the previous 2 centuries, but Voyager 2 provided the first close-up views of these icy worlds, revealing surfaces that bore the scars of ancient impacts and in some cases showed evidence of geological activity that had reshaped the terrain long after the moons had formed. Of all the moons of Uranus, Miranda presented the most remarkable and unexpected surface, a chaotic landscape of jumbled terrains and dramatic geological features that seemed to defy explanation. This small moon, only about 470 kilometers in diameter, displayed regions of ancient cratered terrain alongside younger areas marked by ridges and grooves and peculiar chevron-shaped patterns, as though the moon had been assembled from several different bodies or had been broken apart and reassembled in some violent episode of its distant past. The most striking feature revealed by the Voyager cameras was a towering cliff known as Verona Rupes, which rises approximately 20 kilometers from its base, making it the tallest known cliff in the solar system. An object dropped from the top of Verona Rupes would fall for several minutes before reaching the bottom. So weak is the gravity of this small and distant moon, and the sheer face of the cliff stretches across the landscape like the edge of a broken world. Scientists have proposed various explanations for the tortured surface of Miranda, including the possibility that the moon was shattered by a large impact and then gravitationally reassembled from the scattered pieces, creating the patchwork of different terrains that Voyager observed during its fleeting passage. The signal sent back to Earth from Voyager 2 during the Uranus encounter took 2 hours and 45 minutes to travel the distance from the spacecraft to the receiving antennas, a one-way light travel time that meant the mission controllers had to wait nearly 6 hours for a round-trip communication with their distant ambassador. This delay made real-time control of the spacecraft impossible, and the entire encounter was conducted by pre-programmed instructions uploaded days or weeks in advance, with the spacecraft autonomously executing its observations and maneuvers according to a precise timeline stored in its computer memory. The Voyager team had prepared extensively for this encounter, testing the planned observations in simulations and refining the timing of each camera exposure and instrument reading to make the best use of the brief hours during which the spacecraft was close enough to observe the planet and its moons and rings. Every image had to be planned, every measurement had to be scheduled, and when the moment of closest approach arrived, the team could only wait and trust that their preparations had been sufficient and that the spacecraft would perform as expected in the cold and distant darkness beyond Saturn. The data returned from Uranus transformed what had been a small and distant blur in even the largest telescopes into a real and complex world, a planet with weather and a magnetic field and a family of moons and rings, a place that existed in all its strangeness whether or not any human eye had ever beheld it clearly. Voyager 2 remained at Uranus for only a few hours before continuing on its outward journey toward the most distant encounter of all. But in those brief hours it gathered more information about the tilted ice giant than all the previous centuries of astronomical observation combined. The spacecraft left behind a planet that remained as remote and as cold as it had ever been, spinning on its side in the darkness at the edge of the solar system, its blue-green face turned toward the faint and distant sun, its rings and moons circling in their tilted orbits, and its deep magnetic field wobbling through space in patterns that scientists are still working to understand. On the 25th day of August in the year 1989, after 12 years of traveling through the darkness between worlds, Voyager 2 arrived at Neptune, the eighth and most distant of the major planets, a world so far from the Sun that noon there appears as dim as twilight here on Earth, and the spacecraft's arrival marked the completion of an extraordinary journey that had begun exactly 12 years earlier, to the very day when Voyager 2 had lifted off from Cape Canaveral on a warm Florida morning with no certainty that it would ever reach this pale blue destination at the edge of the known solar system. The journey to Neptune had required patience of a kind that is difficult for us to fully appreciate in our era of instant communication and rapid travel, for the spacecraft had been sailing through the void for more than a decade, passing Jupiter in 1979, Saturn in 1981, and Uranus in 1986, gathering speed and scientific treasures at each encounter, while the engineers and scientists on Earth grew older and wiser alongside their mechanical emissary, learning to coax ever more capability from instruments that had been designed and built when the world was a rather different place. Neptune itself had been a mystery wrapped in distance, visible from Earth only as a small blue disk even through the most powerful telescopes, its weather patterns and moons largely unknown, its rings suspected but not confirmed, and the entire scientific community held its breath as Voyager 2 drew closer and began to reveal what no human eyes had ever witnessed in any detail: the face of a world that takes 165 Earth years to complete a single orbit around our Sun. The first surprise was the Great Dark Spot, a massive storm system that appeared in the spacecraft's cameras as the planet grew larger in its field of view, and this enormous atmospheric disturbance proved to be roughly the size of our own Earth, a swirling vortex of gases moving through Neptune's upper atmosphere with a stately and terrible beauty that seemed almost gentle from a distance of millions of kilometers but which contained winds of extraordinary violence. These winds, measured by tracking the movement of smaller cloud features around and within the Great Dark Spot, were found to reach speeds of approximately 1,500 miles per hour, which represented the fastest winds ever recorded on any planet in our solar system, faster than the fierce bands of Jupiter, faster than the equatorial jets of Saturn, faster than anything the meteorologists of Earth had ever imagined possible in a planetary atmosphere. And yet, from the serene perspective of Voyager 2's cameras, the storm appeared almost peaceful, a dark oval drifting through bands of pale blue and white. The intensity of these winds seemed almost paradoxical given Neptune's tremendous distance from the Sun, For one might reasonably expect that a world receiving so little solar energy would be a quiet and sluggish place, its atmosphere barely stirring in the dim light. And yet Neptune proved to be remarkably active, with its internal heat driving powerful convection currents that generated weather systems of breathtaking violence. A reminder that the outer planets operate by rules that we are still working to fully understand. As Voyager 2 drew ever closer to Neptune, the navigation team on Earth faced perhaps their greatest challenge of the entire mission, for the spacecraft needed to thread a precise path between the planet and its largest moon, Triton, passing close enough to both to gather detailed scientific data while avoiding the gravitational perturbations and potential hazards that such a close approach would entail. And the margin for error was vanishingly small. The engineers sometimes described this maneuver as a hole-in-one shot, borrowing the language of golf to convey the precision required. For after traveling nearly 4.5 billion kilometers through space, Voyager 2 needed to arrive at exactly the right point at exactly the right time, threading between planet and moon like a needle passing through the eye of another needle. And any significant error accumulated over those 12 years of flight would have resulted in a far less productive encounter, or perhaps no encounter at all. At closest approach, Voyager 2 passed just 4,950 kilometers above the tops of Neptune's clouds, a distance that seems almost recklessly close when one considers the planet's powerful gravity and the valuable cargo of scientific instruments that the spacecraft carried. And from this intimate vantage point, the cameras and sensors gathered data of extraordinary quality, revealing details in the atmosphere and measuring properties of the magnetic field that could never have been detected from a more cautious distance. The 4-hour light time delay added another layer of complexity to the encounter, for any command sent from Earth would take 4 hours to reach the spacecraft, and any response or confirmation would take another 4 hours to return, meaning that the navigation team could not make real-time corrections during the closest approach phases, and Voyager 2 had to execute its carefully planned observation sequences autonomously, trusting in the programming that the engineers had uploaded days and weeks in advance. Among the discoveries made during the Neptune encounter were 6 previously unknown moons, small worlds of ice and rock that had escaped detection by Earth-based telescopes, but which revealed themselves to Voyager 2's patient gaze. And these new additions to Neptune's family of satellites ranged in size from modest irregular bodies to more substantial spheroids, each with its own orbital characteristics and surface properties waiting to be studied by future missions that may not arrive for many decades yet. The spacecraft also confirmed the existence of 4 rings around Neptune, delicate structures of dust and ice particles that had been suspected from Earth-based observations, but which now revealed themselves in all their subtle beauty. Faint arcs of material orbiting the planet in patterns that suggested ongoing gravitational interactions with the inner moons, a reminder that even at the edge of the solar system, the dance of gravity continues in its intricate and endless choreography. But perhaps the most remarkable discoveries awaited at Triton, Neptune's largest moon and the final solid body that Voyager 2 would visit on its grand tour of the outer solar system, a world that proved to be even stranger and more fascinating than anyone had dared to hope when the mission was first conceived all those years ago in the optimistic days of early space exploration. Triton orbits Neptune in the wrong direction, moving clockwise when viewed from above the planet's north pole, while all of Neptune's other major satellites move counterclockwise. And this retrograde orbit immediately suggested to planetary scientists that Triton had not formed in place alongside Neptune, but had instead been captured from elsewhere, probably from the Kuiper Belt, that vast reservoir of icy bodies that extends beyond Neptune's orbit into the outer darkness of the solar system. The capture of such a large body, Triton being nearly 3,000 kilometers in diameter, would have been a violent and dramatic event in the early history of the Neptunian system, and the gravitational energy released during the capture and subsequent circularization of Triton's orbit would have generated enormous amounts of heat within the Moon's interior, melting much of its icy substance and perhaps creating a subsurface ocean that may persist to this day beneath the frozen landscape that Voyager 2 photographed during its brief but productive flyby. As the spacecraft approached Triton, its cameras revealed a world of surprising complexity and beauty, with a surface unlike anything seen elsewhere in the solar system, a frozen landscape of cantaloupe terrain, so named because its cellular pattern of ridges and depressions resembles the skin of a cantaloupe melon, and smooth plains of nitrogen ice that reflected the dim sunlight with a pale ethereal glow. The southern polar cap of Triton appeared in the images as a vast expanse of pinkish material, frozen nitrogen ice tinted by the presence of organic compounds called tholins, which form when simple molecules like nitrogen and methane are exposed to ultraviolet radiation from the sun. And this pink polar cap gave Triton an unexpectedly colorful appearance, a blush of warmth in a world of almost unimaginable cold. For Triton proved to be the coldest place ever measured in the solar system, with a surface temperature of approximately minus 235 degrees Celsius, just 38 degrees above absolute zero. A cold so profound that most familiar substances would be as hard as rock, and the atmosphere itself, thin as it is, consists of nitrogen that hovers just above its freezing point, ready to condense onto the surface at the slightest cooling. And yet, despite this extreme cold, Triton was not a dead world, for Voyager 2's cameras captured evidence of active geology in the form of nitrogen geysers, plumes of gas and dark material shooting upward from the surface to heights of approximately 8 kilometers before being carried sideways by the thin winds of Triton's tenuous atmosphere, creating dark streaks across the pink southern polar cap like the marks of some vast calligraphic brush. These geysers, driven perhaps by the feeble warmth of sunlight penetrating the transparent nitrogen ice and heating darker material beneath, represented the first evidence of active geological processes on any icy body in the outer solar system, a discovery that would later be echoed by observations of similar activity on Saturn's moon Enceladus and hints of geological youth on several other distant worlds. The mechanism powering Triton's geysers appears to involve a kind of solid-state greenhouse effect, wherein sunlight passes through the transparent surface ice and warms darker material below, causing nitrogen ice at depth to sublimate directly into gas, and this gas builds up pressure until it finally erupts through vents in the surface, carrying dark particles with it and creating the plumes that Voyager 2 photographed with such serendipitous timing during its brief passage through the Neptunian system. As Voyager 2 completed its observations and prepared to depart the Neptune system, it captured one final series of images that would become iconic in the annals of planetary exploration: photographs of the crescent Neptune, the planet's illuminated edge glowing against the darkness of space as the spacecraft looked back toward the inner solar system, a perspective that no human eye would ever see directly, but which Voyager 2 could share with all of us through the patient transmission of its digital data across the vast gulf of space. The gravitational encounter with Neptune had also given Voyager 2 a final boost in speed, accelerating the spacecraft to approximately 27 kilometers per second as it bent around the planet and was flung outward toward interstellar space. And this increase in velocity would carry Voyager 2 away from the Sun forever, joining its twin Voyager 1 in the long, slow journey toward the stars that neither spacecraft would reach for many thousands of years. This remains, to this day, humanity's only close encounter with Neptune, for no other spacecraft has visited this distant world in the more than 3 decades since Voyager 2's passage. And though mission planners have proposed various Neptune orbiters and atmospheric probes, none have yet been funded and built, leaving the data gathered during those few precious hours of closest approach in August 1989 as our primary source of detailed information about the eighth planet and its fascinating system of moons and rings. The knowledge gained during the Neptune encounter continues to inform our understanding of ice giant planets, a class of world that includes both Uranus and Neptune and which appears to be common among the exoplanets discovered orbiting other stars. And in this sense, Voyager 2's observations of Neptune provide a template for understanding countless similar worlds scattered throughout our galaxy, places we may never visit but which we can begin to comprehend through the lens of what we learned during that remarkable summer of 1989. As you settle further into the warmth of your bed, perhaps you might imagine the pale blue light of Neptune shining in the darkness of the outer solar system, its storms endlessly swirling, its rings slowly processing, its captured moon Triton patiently orbiting in its backwards direction while occasional geysers send dark plumes into the thin cold sky, all of it continuing in its ancient rhythms long after Voyager 2 departed for the final frontier beyond, where the spacecraft continues its journey even now, carrying memories of Neptune across the void between the stars. In the early months of 1990, when Voyager 1 had already completed its grand encounters with Jupiter and Saturn and was drifting ever further from the realm of the planets, a rather unusual request made its way through the corridors of the Jet Propulsion Laboratory in Pasadena, California. The astronomer Carl Sagan, who had served on the imaging team for the Voyager missions since their inception, had been quietly campaigning for several years to turn the spacecraft's cameras around, to point them not outward into the unknown depths of interstellar space, but backward, toward home, toward the inner solar system and the small blue world from which Voyager had departed more than 12 years earlier. It was, in the language of mission planning, an unusual request, and it met with considerable hesitation from those responsible for the spacecraft's continued operation and scientific productivity. The reluctance from NASA administrators and mission planners was not born of indifference or lack of imagination, but rather from practical considerations that governed every decision made about the aging spacecraft. Voyager 1 was by that point approximately 6 billion kilometers from Earth, a distance so vast that it takes some quiet contemplation to begin to appreciate. At that remove, roughly 40 times the distance between Earth and the Sun, the inner planets would appear as nothing more than pinpricks of light, if they appeared at all. The scientific value of such images, from a strictly technical standpoint, was essentially nil. The cameras aboard Voyager had been designed to capture the swirling cloud bands of Jupiter and the intricate ring structure of Saturn, not to photograph distant specks that would register as mere fractions of a single pixel on the imaging sensors. There would be no new geological features to map, no atmospheric dynamics to study, no moons to catalogue. The images would tell us nothing we did not already know about the planets themselves. Moreover, there was a genuine concern about the safety of the camera system. To photograph the inner solar system from Voyager's position meant pointing the cameras in the general direction of the Sun, and though the Sun would appear far smaller from that distance than it does from Earth, it remained an intensely bright object capable of damaging the sensitive charge-coupled devices that formed the heart of the imaging system. The CCDs, as these electronic sensors are commonly known, could potentially be overwhelmed or permanently damaged by exposure to direct or near-direct sunlight, even sunlight diminished by the vast distance. It was a risk that seemed difficult to justify for images of questionable scientific merit. Yet Carl Sagan persisted, gently and thoughtfully, as was his way. His argument was not primarily scientific in the narrow sense, but rather humanistic, philosophical, even spiritual in its orientation. He believed that such an image, a photograph of Earth taken from the outer reaches of the solar system, would hold profound meaning for the people of Earth, that it would offer a perspective unavailable through any other means, a view of our world as a tiny and isolated point of light in the cosmic darkness. He understood, perhaps better than most, that science serves not only to expand our knowledge of the physical universe but also to reshape our understanding of our place within it, and he felt certain that this image, however small and seemingly insignificant, would accomplish something that no amount of data about planetary atmospheres or magnetic fields could achieve. In time, Sagan's persistence was rewarded, and the decision was made to proceed with what became known as the family portrait, a series of images that would capture not just Earth but several of the other planets of our solar system, a mosaic of our cosmic neighborhood as seen from its outermost margins. The date chosen for this endeavor was the 14th of February, 1990, Valentine's Day as it happens, though this coincidence appears to have been more a matter of orbital geometry and mission scheduling than romantic symbolism. On that day, commands were transmitted from Earth to Voyager 1, instructions that would travel at the speed of light across 6 billion kilometers of empty space, taking approximately 5.5 hours to reach the spacecraft. These commands directed the imaging system to execute a carefully planned sequence of exposures, turning to capture Mercury, Venus, Earth, Mars, Jupiter, and Saturn in a series of 60 frames that would together form a grand portrait of the solar system. The commands were received by Voyager 1 and executed faithfully by the spacecraft's onboard systems, and the cameras, which had been dormant for some time, whirred back to life one final time. The imaging sequence required careful planning to avoid pointing the cameras too close to the Sun while still capturing the target planets, and even so, some of the images would be affected by scattered light within the camera optics, rays and streaks of sunlight that would cross the frames in pale bands. The exposures were made. The data was recorded on the spacecraft's tape recorder, and then began the long process of transmitting that data back to Earth across the vast gulf of space. At a distance of 6 billion kilometers, the transmission of data is not a swift affair. The radio signals from Voyager 1, traveling at the speed of light, required approximately 6 to 4 minutes to traverse the distance between the spacecraft and the receiving antennas of the deep space network on Earth. Each image had to be transmitted bit by bit, the data trickling across the solar system at a rate that would seem agonizingly slow by the standards of modern internet connections. The process of receiving and assembling the complete family portrait took considerable time and patience, but eventually the images arrived, were processed, and were revealed to the waiting scientists and to the world. Most of the planets appeared as small bright points against the blackness of space, recognizable only because the mission planners knew precisely where to look. Mars was too faint to be captured, lost in the glare of scattered sunlight, and Mercury was similarly elusive, too close to the Sun for the cameras to safely image. But there, in one of the frames, was Earth, and it was this image that would capture the imagination of the world and cement the family portrait in the collective memory of our species. Earth appeared as a pale blue dot, and when one says dot, one means this quite literally, for our planet occupied approximately 12/100ths of a single pixel in the image, a mote so small that it could easily be mistaken for a flaw in the sensor or a cosmic ray strike on the detector. The planet was suspended in a scattered ray of sunlight, one of several colored bands that crossed the image due to light bouncing within the camera's optical system. This accidental framing, the tiny Earth caught within a beam of light against the darkness, gave the image an almost painterly quality, as though some cosmic artist had deliberately composed the scene to emphasize both the fragility and the isolation of our world. When the image was released to the public, Carl Sagan spoke about it with the quiet eloquence that had made him such an effective communicator of scientific ideas to general audiences. He reflected on what it meant to see our world from such a distance, to comprehend that everything we know, every person who has ever lived, every civilization that has risen and fallen, every act of kindness and cruelty, every triumph and tragedy in the long story of human existence, had taken place on that tiny point of light, smaller than a grain of sand held at arm's length, easily overlooked, easily forgotten in the immensity of the cosmos. Several years later, in 1994, Sagan published a book titled Pale Blue Dot, which took its name from this image and explored the themes of cosmic perspective and human significance that the photograph so powerfully evoked. In this book, he penned what has become one of the most quoted passages in the literature of space exploration, a meditation on the meaning of that distant image. He wrote of Earth as a mote of dust suspended in a sunbeam, and he reflected on how the vastness of space underscores the importance of the only home we have ever known. He considered how the great rivers of blood that have been spilled throughout history were shed by generals and emperors seeking to become momentary masters of a fraction of that dot, and how the posturings of our leaders seem absurd when viewed against the backdrop of cosmic immensity. The passage continues in this contemplative vein, suggesting that the photograph should serve as a reminder of our responsibility to deal more kindly with one another and to preserve and cherish the pale blue, the only home we have ever known. These words have resonated deeply with readers and have been quoted countless times in discussions of environmentalism, philosophy, and the human condition. The pale blue dot image and Sagan's accompanying reflection have become touchstones for a particular kind of cosmic humility, a recognition that our world, for all its importance to us, occupies no special place in the grand architecture of the universe. The cultural impact of this image has been considerable and has grown in the decades since it was first released. It has appeared in documentaries and museum exhibits, on posters and book covers, in classrooms and lecture halls around the world. It has been invoked in discussions of climate change and environmental stewardship as a reminder that there is no backup planet, no alternative Earth waiting to receive us if we render our own world uninhabitable. The image speaks to something deep in the human psyche, our need to understand our place in the larger scheme of things, our yearning for perspective in a world often consumed by the immediate and the local. Philosophers and theologians have found in the pale blue dot a visual representation of ideas that have been expressed in various forms throughout human history. The notion that our concerns, however pressing they seem to us, are small in the context of eternity. The recognition that we are all fellow travelers on a small craft adrift in an incomprehensibly vast ocean of space and time. The image does not diminish us so much as it contextualizes us, placing human existence within a frame that encourages both humility and a certain kind of wonder. Shortly after the family portrait images were captured and transmitted, the decision was made to power down Voyager 1's imaging system permanently. This was not done out of any dissatisfaction with the camera's performance, but rather as a necessary measure to conserve the spacecraft's dwindling electrical power. The radioisotope thermoelectric generators that provide Voyager with electricity produce less power with each passing year as the plutonium-238 fuel decays, and difficult choices must be made about which instruments to keep active. The cameras, having completed their planetary survey and having taken this final backward glance at the solar system, were no longer needed. Other instruments, those capable of measuring magnetic fields and charged particles and the tenuous plasma of the outer heliosphere, would continue to operate, gathering data about regions of space that no human-made object had ever visited. The final commands to the imaging system were transmitted and received, and the cameras fell silent, their work complete. It is a curious thing to contemplate, that a machine built by human hands could journey so far from home, could reveal such wonders as the volcanoes of Io and the methane lakes of Titan, and could then, at the end of its photographic career, turn back to capture a single image that would move the human heart more profoundly than any of its scientific achievements. The cameras aboard Voyager 1 had been designed to explore the outer planets, and they did so magnificently, but their final act was to offer us a mirror, a reflection of ourselves as seen from the shores of the cosmic ocean. The pale blue dot remains, decades later, one of the most significant photographs ever taken, not for its technical quality or its scientific content, but for what it reveals about who we are and where we stand in the universe. It is an image that invites quiet contemplation, that asks us to consider what it means to be human on a small world in a vast cosmos, that suggests, gently and without insistence, that we might do well to treat one another with greater kindness and to care for the pale blue that is, for now and for the foreseeable future, the only home our species has ever known. On the 25th of August, in the year 2012, a small spacecraft no larger than a compact car drifted silently across an invisible threshold that no human-made object had ever approached before, and in doing so, it became the first emissary from Earth to touch the space between the stars. Voyager 1, that patient traveler launched some 35 years earlier from a Florida launch pad, had finally crossed the heliopause, the boundary where our sun's influence gives way to the broader currents of the Milky Way galaxy itself. This crossing happened without fanfare at the moment of its occurrence, for the spacecraft simply continued onward as it had done for decades, its instruments recording data that would take many months for scientists back on Earth to fully understand and confirm. The distance from our sun at this crossing was approximately 122 astronomical units, which is to say 122 times the distance between Earth and the sun, a measurement that translates to roughly 18 billion kilometers of empty space traversed since that September morning in 1977, when Voyager 1 first lifted off into the Florida sky. The confirmation of this historic crossing did not come quickly, as the nature of such boundaries in space is far more subtle and gradual than the sharp borders we draw on terrestrial maps. NASA made the official announcement on the 12th of September, 2013, more than a year after the actual crossing had taken place, and this delay reflected the careful and methodical work required to interpret the data streaming back from such an enormous distance. The signals from Voyager 1, traveling at the speed of light, still required more than 17 hours to reach the Deep Space Network antennas on Earth, and the information they carried needed to be compared against decades of theoretical predictions about what interstellar space should look like. Scientists had long debated what signatures would indicate a true crossing of the heliopause, and the data ultimately revealed a picture both familiar and surprising, confirming some predictions while challenging others in ways that would reshape our understanding of the sun's influence on its cosmic neighborhood. The plasma wave science instrument aboard Voyager 1 provided perhaps the most compelling evidence that the spacecraft had indeed entered interstellar space, though this confirmation came through a somewhat indirect and patient method of observation. This instrument, designed to measure the oscillations and vibrations in the plasma surrounding the spacecraft, detected something remarkable in the months following the crossing. When a coronal mass ejection, which is a large eruption of solar material and magnetic field from the sun's corona, swept past Voyager 1's location in the spring of 2013, it caused the surrounding plasma to vibrate and oscillate in measurable ways. These plasma oscillations allowed scientists to calculate the density of the material through which Voyager 1 was traveling, and the results were striking. The plasma surrounding the spacecraft was approximately 40 times denser than the solar wind plasma that had bathed Voyager 1 throughout its long journey through the heliosphere, a density consistent with the cold, dense plasma of interstellar space that theoretical models had long predicted should exist beyond the heliopause. This coronal mass ejection, a somewhat violent event by the Sun's standards, served an unexpectedly gentle purpose in helping scientists understand where Voyager 1 had traveled. The eruption had occurred many months earlier at the Sun itself, and the wave of material and energy had expanded outward through the solar system at speeds that, while fast by human standards, still required considerable time to reach such distant regions. When this wave finally arrived at Voyager 1's location and set the surrounding plasma vibrating like a struck tuning fork, the frequency of those vibrations revealed the density of the medium. And that density told researchers they were no longer measuring the Sun's own extended atmosphere, but rather the material that fills the spaces between stellar systems. It was a confirmation delivered not through dramatic revelation, but through the patient accumulation of evidence, the careful matching of observation to theory, and the willingness to wait for the right conditions to provide clarity. The journey to this threshold had been a gradual one, marked by several intermediate regions that scientists had not fully anticipated when Voyager 1 was launched. In December of 2004, the spacecraft crossed the termination shock, that turbulent boundary where the solar wind slows from supersonic to subsonic speeds as it begins to feel the pressure of the interstellar medium pushing back against it. Beyond this point lay the aleo sheath, a thick region of slower, denser, and more turbulent solar wind that Voyager 1 would spend the next 8 years traversing. This aleo sheath proved to be a complex and dynamic environment, filled with magnetic bubbles and regions of varying particle density that challenged earlier models of a relatively smooth transition zone. The spacecraft's instruments recorded fluctuations in magnetic field strength and direction, variations in the flux of charged particles, and other signatures of a boundary region that was anything but simple or static. In the months leading up to the actual heliopause crossing, Voyager 1 passed through yet another unexpected region that scientists came to call the magnetic highway, a name that evokes images of orderly lanes of traffic moving in consistent directions. In this zone, detected beginning in August of 2012, the magnetic field lines appeared to become more orderly and connected to the interstellar magnetic field beyond, allowing charged particles from inside the heliosphere to escape outward, while cosmic rays from interstellar space streamed inward with greater ease. The magnetic field strength remained elevated, and its direction stayed consistent with the Sun's magnetic field, rather than shifting to the orientation expected in true interstellar space. This magnetic highway represented a kind of transitional corridor, a final antechamber before the main boundary, and its discovery added another layer of complexity to our understanding of how the heliosphere interacts with its galactic surroundings. The detection of the actual boundary change relied on several complementary signatures that, taken together, painted a convincing picture of interstellar arrival. Scientists observed a sudden and sustained increase in the flux of galactic cosmic rays, those high-energy particles that originate from distant supernovae and other energetic events throughout the galaxy. These cosmic rays had previously been partially blocked by the magnetic shield of the heliosphere, and their increased intensity indicated that Voyager 1 had moved beyond that protective bubble. Simultaneously, the instruments recorded a dramatic drop in the flux of lower-energy particles originating from the Sun itself, particles that had accompanied the spacecraft throughout its long journey and now found themselves unable to penetrate into the interstellar medium with the same ease. This combination of increasing galactic cosmic rays and decreasing solar particles created a kind of particle fingerprint that matched theoretical predictions for the heliopause crossing, though the magnetic field behavior remained puzzling and somewhat contrary to expectations for some time afterward. In the years since that historic crossing, Voyager 1 has continued its outward journey at a speed of approximately 17 kilometers per second relative to the Sun, steadily increasing its distance from our home star with each passing moment. The current distance of the spacecraft now exceeds 160 astronomical units, a number that grows larger with each day, each hour, and each minute as the patient probe continues its endless drift into the galaxy. The spacecraft still communicates with Earth, still returns data about the conditions in interstellar space, and still carries with it that golden record containing sounds and images of Earth and its inhabitants. The power from its radioisotope thermoelectric generators continues to diminish with each passing year, and mission controllers have gradually shut down non-essential instruments to extend the mission for as long as possible. But Voyager 1 remains an active scientific instrument even now, decades after it might reasonably have been expected to fall silent. Voyager 2. The sister spacecraft launched 16 days before Voyager 1 but traveling on a slower trajectory due to its more extensive planetary tour, followed its sibling into interstellar space on the 5th of November, 2018. This second crossing occurred at a different location relative to the heliosphere, at a distance of approximately 119 astronomical units from the Sun, slightly closer than Voyager 1's crossing point. The difference in crossing distances, while seemingly small in the context of such enormous scales, carries significant scientific implications. It suggests that the heliosphere is not a perfectly symmetrical bubble centered on the Sun, but rather a distorted shape, compressed on one side by the pressure of interstellar material and stretched on the other by some combination of factors that scientists are still working to understand fully. The boundary conditions encountered by Voyager 2 differed from those measured by Voyager 1 in several notable ways, providing researchers with comparative data that a single crossing could never have supplied. Voyager 2's plasma science instrument, which had remained functional while Voyager 1's equivalent had failed decades earlier, allowed direct measurements of the solar wind plasma right up to and through the heliopause crossing. These measurements revealed that the heliopause at Voyager 2's crossing location was somewhat thinner and sharper than the boundary Voyager 1 had traversed, with a more abrupt transition between solar and interstellar plasma densities. The magnetic field behavior also showed some differences between the two crossing locations, though both spacecraft found that the interstellar magnetic field direction did not change as dramatically as some models had predicted it would. The asymmetry of the heliosphere revealed by these two crossings has prompted new thinking about how our Sun interacts with the local interstellar medium through which it travels. The solar system moves through the galaxy at a speed of approximately 23 kilometers per second, and this motion creates a kind of bow wave or compressed region ahead of the heliosphere's direction of travel, while the trailing edge is stretched and elongated like the tail of a comet. The different locations of the Voyager crossings allowed scientists to sample different regions of this asymmetric structure, with Voyager 1 exiting through the more compressed nose region and Voyager 2 departing through a flank where the boundary conditions were somewhat different. Together, the two spacecraft provide a kind of stereoscopic view of the heliosphere's edge, allowing for comparisons that illuminate the three-dimensional shape and dynamic behavior of our Sun's protective bubble. The heliosphere itself, that vast region of space dominated by the Sun's magnetic field and outflowing solar wind, serves as a kind of protective cocoon for the solar system, deflecting and moderating some portion of the cosmic radiation that would otherwise stream freely through our planetary neighborhood. The data from both Voyager spacecraft have confirmed that this boundary, while not a solid wall, does represent a real transition in the radiation environment, with higher levels of galactic cosmic rays beyond the heliopause than within it. Understanding this boundary has implications for future human exploration of deep space, for the long-term habitability of the solar system, and for our comprehension of how stellar systems generally interact with the galactic environments through which they move. Both Voyager spacecraft continue their journeys now, each moving outward on its own trajectory, each carrying instruments that still function and transmitters that still send their faint signals back across the enormous gulf of space to waiting antennas on Earth. They are no longer explorers of planets, having completed those missions long ago, but rather explorers of the space itself, the vast emptiness that separates stellar systems from one another. The data they return tell us about the density and temperature of interstellar plasma, the strength and direction of galactic magnetic fields, the flux and energy spectrum of cosmic rays, and countless other details about a region of space that no human will visit for generations yet to come. They have become our most distant outposts, our farthest flung instruments, and they continue their patient work of measurement and transmission even as the power that sustains them slowly fades with each passing year. The distances involved in these crossings remain difficult for the human mind to fully grasp, even when expressed in the convenient units of astronomical units or light hours. 122 astronomical units means that light itself, the fastest thing in the universe, requires more than 17 hours to travel from the Sun to the point where Voyager 1 crossed into interstellar space. The instructions sent from Earth to the spacecraft take equally long to arrive, and the data returned takes equally long to reach us, creating a round-trip communication time of more than 34 hours at current distances. Yet even these enormous numbers represent only the barest beginning of the journey to the nearest star system, Alpha Centauri, which lies some 270,000 astronomical units away. Voyager 1, at its current speed, will not pass within any significant distance of another star for some 40,000 years, and by that time its instruments will long since have fallen silent, and its golden record will carry its message of human existence as a quiet, drifting artifact in the dark between stars. And so we come now to the people who remain here on Earth, the ones who have spent decades listening for the faintest of whispers from spacecraft that have traveled farther than any human-made object in history, and we find ourselves in the quiet rooms of mission control, where the longest vigil in the history of space exploration continues even now, even as you listen to these words. In the small hours of the night somewhere on our spinning planet, someone is always awake, always listening for Voyager. The Deep Space Network is the name given to the collection of radio antennas that NASA uses to communicate with spacecraft throughout the solar system and beyond. And this network consists of 3 stations positioned roughly 120 degrees apart around the globe, so that as the Earth rotates on its axis, at least one station is always able to point toward any spacecraft at any time of day or night. And these 3 stations are located in Goldstone in the Mojave Desert of California, in Madrid in Spain, and in Canberra in Australia. And if you were to look at a globe and mark these 3 locations, you would see that they form a rough triangle around the Earth, ensuring continuous coverage of the entire sky. And this arrangement means that the Voyager spacecraft are never truly alone, never out of reach of human contact, though the reach has grown so very long indeed. The antennas at these stations are quite large, as you might imagine they would need to be to catch signals from so great a distance, and the largest of them measure 70 meters across, which is to say they are wider than the length of a football field. And these enormous dishes must be pointed with extraordinary precision toward a location in the sky where the spacecraft was many hours ago. because the signals take so long to travel that by the time they reach Earth, the Voyager craft have moved on from where they were when they sent the message, and so the mathematics of aiming these dishes becomes a gentle exercise in predicting the past, if such a thing can be imagined, calculating where the spacecraft will have been when the signals that are arriving now were first transmitted. The signals themselves are remarkably faint, and this is one of the most humbling aspects of the entire endeavor, because each Voyager spacecraft transmits its data using a radio transmitter that operates at just 23 watts of power, which is approximately the same amount of energy used by a small light bulb in a refrigerator, the sort of bulb that illuminates the contents when you open the door late at night looking for a glass of milk. And this tiny amount of power must travel across billions of miles of empty space, spreading out as it goes, becoming thinner and more diffuse with every passing moment, until by the time it reaches Earth it has become almost impossibly weak. And yet the great dishes of the deep space network are sensitive enough to detect even this faint whisper, to pluck it from the background noise of the cosmos and decode its meaning. The computers aboard the Voyager spacecraft are a testament to the engineering capabilities of the 1970s. And when we consider their specifications by modern standards, we find something rather touching in their simplicity, because each spacecraft carries computer systems with a total memory of just 69.63 kilobytes, which is less memory than would be required to store a single modern email with an attachment, less than a small photograph taken on a mobile phone. And yet these modest computers have managed the operations of the spacecraft for more than 4 decades, executing their programs faithfully, responding to commands from Earth, and making autonomous decisions when necessary, all with resources that would seem laughably inadequate by today's standards. And there is something rather wonderful in the reminder that sophisticated technology is not always necessary to achieve remarkable things, that simplicity and reliability can be virtues of the highest order. The rate at which data can be transmitted from the Voyager spacecraft has also diminished over the years, dropping to just 160 bits per second in the most recent communications, which means that if you wish to send a single photograph from Voyager at this rate, it would take many hours to transmit, each pixel arriving slowly, one after another, like drops of water from a barely open tap. And this gradual accumulation of information requires patience of a sort that is increasingly rare in our modern world of instantaneous communication. And yet the controllers at Mission Control accept this pace with equanimity, understanding that when you are communicating across 12 billion miles, there is no rushing. There is only the steady accumulation of data points, each one precious, each one worth waiting for. The people who built the Voyager spacecraft and designed its systems were young engineers and scientists in the 1970s, many of them fresh from university, filled with enthusiasm for the ambitious mission they had been assigned. And as the decades have passed, these original team members have aged alongside their spacecraft, retiring one by one, taking with them irreplaceable knowledge about the systems they designed, the quirks and eccentricities of circuits and software that were created before many of the current NASA staff were even born. And this has presented a particular challenge for the mission, because finding people who understand the technology of that era becomes more difficult with each passing year. And so there has been a careful effort to document knowledge, to train younger engineers in the ways of obsolete systems, to ensure that institutional memory is not lost entirely when the original builders finally lay down their tools. The challenge of maintaining hardware that was designed nearly 50 years ago extends beyond the spacecraft themselves to the ground systems used to communicate with them. And here the mission has encountered difficulties that would be almost comical if they were not so serious, because some of the components needed to keep the ground systems running are no longer manufactured, have not been manufactured for decades, And so the resourceful engineers at the Deep Space Network have been known to search in unusual places for replacement parts, scouring the inventories of museums, browsing the listings on eBay, reaching out to collectors of vintage electronics who might have a working component tucked away in a garage somewhere. And there is something deeply human about this image. The idea that the continued communication with humanity's most distant ambassadors might depend upon finding a particular vacuum tube or integrated circuit in the dusty corner of an antique shop. Suzanne Dodd is the project manager for the Voyager missions, and she oversees a team of just 8 people, which seems an almost impossibly small number when you consider the enormity of what they are responsible for. 2 spacecraft traveling at the edge of interstellar space, requiring constant attention and careful management of dwindling resources. And yet this tiny team, working from the Jet Propulsion Laboratory in Pasadena, California, has proven more than adequate to the task, demonstrating that dedication and expertise can compensate for limited numbers, that a small group of deeply committed individuals can accomplish what larger organizations might find daunting. The power systems aboard the Voyager spacecraft present the most pressing long-term challenge to the mission's continued operation, because the radioisotope thermoelectric generators that provide electricity to the spacecraft are slowly losing their potency as the plutonium-238 within them undergoes radioactive decay. And these power sources now produce approximately 40% less electricity than they did at launch, a decline that continues at a steady rate year after year. And current estimates suggest that by sometime between 2025 and 2030, the power output will drop below the minimum level required to operate any scientific instruments at all, at which point the spacecraft will fall silent, not because they have been destroyed or have malfunctioned, but simply because they no longer have the energy to send their signals home. To extend the useful life of the spacecraft as long as possible, the mission team has undertaken a careful program of power management, systematically shutting down instruments and systems that are no longer essential, choosing which capabilities to sacrifice so that others might continue a little longer. And these decisions are not made lightly, because each instrument represents a unique capability, a way of sensing the environment that surrounds the spacecraft. And to turn one off is to close a window onto the universe, to lose forever the ability to make certain kinds of observations. And yet there is no alternative. The laws of physics are not negotiable, and the plutonium will continue its slow decay regardless of human wishes. Among the strategies employed to conserve power is the careful management of heaters, small electrical devices that keep various components of the spacecraft warm enough to function in the incredible cold of deep space, where temperatures can drop to hundreds of degrees below zero. And by turning off heaters in certain areas and allowing those regions to grow cold, the mission team has been able to redirect precious watts of electricity to the scientific instruments that continue to operate. And this has required detailed analysis of each subsystem, determining which components can tolerate extreme cold without permanent damage and which absolutely must be kept warm. A delicate balancing act performed across billions of miles. The ability to upload new software to the spacecraft has been one of the most valuable tools available to the mission team, allowing them to modify the behavior of the onboard computers, to fix problems that were never anticipated when the spacecraft were designed, to implement new power-saving measures, and to adapt to the changing conditions of interstellar space. And these software uploads are themselves remarkable achievements, requiring careful planning and testing to ensure that the new code will function correctly, because a mistake could potentially disable the spacecraft entirely, leaving it unable to receive further commands. And so each upload is approached with extreme caution, verified and re-verified before being transmitted across the vast distance, the commands traveling for nearly a day before reaching their destination. followed by an anxious wait for confirmation that all has gone according to plan. The time delay in communication with the Voyager spacecraft is now more than 22 hours in each direction, which means that a round-trip communication, sending a command and receiving a response, takes nearly 2 days. And this delay fundamentally shapes the way the mission is operated, because there is no possibility of real-time control, no way to make quick adjustments in response to unexpected events. And so the spacecraft must be trusted to operate autonomously for extended periods, following their programmed instructions faithfully, making decisions on their own when circumstances require it. And the mission team must practice a kind of patience that is almost meditative in nature, sending their commands into the void and then waiting for the response that will eventually come. The 3 stations of the Deep Space Network take turns tracking the Voyager spacecraft as the Earth rotates beneath the stars, handing off responsibility from one to another in a continuous relay that has been maintained for more than 4 decades. And the controllers at each station have developed their own relationships with the distant travelers, their own sense of connection to machines that they will never see except as faint points of data on their screens. And there is something beautiful in this vigil, in the idea that somewhere in the world at this very moment, someone is listening for Voyager. Someone is watching the screens and waiting for the next packet of data to arrive, keeping faith with spacecraft that left Earth before many of them were born. And so the vigil continues, as it has continued through administrations and generations, through technological revolutions that have transformed every other aspect of human life. The same basic task remains, listening for the faint signals that travel across the emptiness of space, decoding the messages that arrive at 160 bits per second, making the decisions that will keep the spacecraft alive for another day, another month, another year. And though the end is now foreseeable, though the power will inevitably fail and the signals will eventually cease, the commitment remains unwavering. The small team of 8 dedicated souls carrying on the work that began so long ago, maintaining the longest vigil in the history of exploration, keeping watch over humanity's most distant messengers as they sail on toward the stars. And so we come now to consider what lies ahead, the long and quiet journey that stretches before these 2 small spacecraft, a journey measured not in years or even centuries, but in timescales that dwarf the whole of human civilization. And it is perhaps a comforting thought, as you settle in and let your breathing slow, that while we rest here on Earth, Voyager 1 and Voyager 2 continue onward through the darkness, moving at speeds that seem immense by earthly standards yet appear almost still against the vast distances between the stars. Voyager 1, the more distant of the pair, travels now at approximately 17 kilometers per second, which sounds rather fast, and indeed it is, fast enough to cross the entire United States in about 4 minutes. And yet at this speed it would still take roughly 18,000 years to travel a single light year, that fundamental unit of cosmic distance that represents how far light itself travels in 1 Earth year. And light, as you may recall from earlier musings, moves at just under 300,000 kilometers every second, which makes Voyager's pace, impressive as it may be, seem rather more modest when set against the enormity of interstellar space. The nearest star to our own Sun is Proxima Centauri, sitting at a distance of approximately 4¼ light years. But Voyager 1 is not heading in that direction, for spacecraft do not choose their paths as ships at sea might adjust their sails, and instead our distant traveler follows the trajectory imparted to it long ago by the gravity assists of Jupiter and Saturn, a path that carries it northward, if we may use such a term in the 3-dimensional ocean of space, out of the plane of the solar system and toward a region of sky in the constellation Camelopardalis, the giraffe, a faint and often overlooked pattern of stars in the northern heavens. in approximately 40,000 years, which is to say roughly 8 times longer than all of recorded human history. Voyager 1 will pass within about 1.6 light-years of a small red dwarf star known as Gliese 445. And while this may sound quite close by cosmic standards, 1.6 light-years still represents a distance of approximately 15 trillion kilometers, and so there will be no close encounter, no dramatic flyby, merely the gentle passage of our small ambassador through a region of space that happens to be somewhat nearer to another star than to our own sun. And by that time, the spacecraft will have been silent for tens of thousands of years, its plutonium long since decayed, its instruments dark, its antenna pointed at nothing in particular, drifting as a cold and quiet artifact through the endless night. Voyager 2, traveling on its own separate course, moves at a slightly slower pace and in a different direction, heading roughly southward from the plane of the ecliptic, and its future appointment is with a rather more famous stellar neighbor. For in approximately 296,000 years, it will pass within about 4 light-years of Sirius, the brightest star in our night sky. That brilliant blue-white beacon in the constellation Canis Major that has guided sailors and inspired poets for as long as humans have looked upward. And it seems somehow fitting that one of our little messengers should eventually drift through the neighborhood of such a celebrated star, though Sirius will not notice, and Voyager 2 will not be aware, for by then both spacecraft and star will simply be matter and energy following their own quiet trajectories through the galaxy. And here is a thought that may carry you gently towards sleep: the recognition that after these stellar encounters, unremarkable as they may be in any physical sense, the Voyager spacecraft will continue onward, not for thousands more years or even millions, but for billions of years, orbiting the center of our Milky Way galaxy just as the Sun itself does, completing one galactic circuit every 230 million years or so. And in this sense, the Voyagers have become permanent features of our galaxy, tiny additions to the countless objects that will slowly around that distant gravitational center, and they will likely persist in some form for longer than our Sun will shine, for longer perhaps than Earth itself will exist as a recognizable planet. But we are getting ahead of ourselves, as it is easy to do when contemplating such timescales, and we should return for a moment to the nearer future, to the mid-2030s, when the final instruments aboard these spacecraft are expected to fall silent at last, for despite their remarkable longevity, the Voyagers cannot continue operating forever, and the limiting factor has always been power. That steady trickle of electricity generated by the radioisotope thermoelectric generators, which convert the heat from decaying plutonium-238 into usable energy. When the Voyagers launched in 1977, each RTG produced about 470 watts of electrical power, roughly enough to illuminate 4 or 5 household light bulbs. And this was more than sufficient to operate the spacecraft's instruments and communications equipment. But radioactive decay is inexorable, and plutonium-238 has a half-life of approximately 87 years, meaning that every 87 years half of the remaining plutonium transforms into other elements, releasing slightly less heat as time goes on. And so the power available to each spacecraft has been declining steadily, year by year, decade by decade. As of now, in the year 2024, the Voyagers produce only about 4 watts of electrical power each, barely enough to power a small nightlight, and the engineers at the Jet Propulsion Laboratory have performed remarkable feats of technical conservation, shutting down heaters and non-essential systems, reprogramming computers to use less energy, squeezing every last bit of useful operation from these aging machines. And yet there will come a point, probably sometime between 2025 and 2036, when there simply is not enough power remaining to run even a single scientific instrument, and the last data transmission will be sent, and the deep space network will listen, and then there will be silence. This moment, when it comes, will be a quiet one, for space missions do not end with fanfare or ceremony. They simply stop responding, and the engineers will send command and receive no reply, and they will try again, and again there will be only the soft hiss of cosmic background noise, and eventually they will note the time in their logs and acknowledge that the mission, after 47 years or 50 years or however long it proves to be, has finally concluded, and Earth will have lost contact with its most distant children. Yet the voyages themselves will not end in that moment, for the spacecraft will continue to exist, cold and silent but structurally intact, and strapped to the side of each one is a 12-inch gold-plated copper disc, the famous Golden Record, that remarkable artifact of human optimism and loneliness that we discussed earlier. And these records were designed not for us, not for any listener who might hear them in our lifetimes or even in the lifetime of our civilization, but for some unimaginably distant future, some encounter that may never occur but which we could not bring ourselves to dismiss entirely. The Golden Records will survive in interstellar space for a very long time indeed, for the environment between the stars is extraordinarily gentle compared to the harsh conditions near planets and suns. There is virtually no atmosphere to cause erosion, no water to promote corrosion, no ultraviolet radiation intense enough to degrade materials quickly, and while there are cosmic rays and micrometeorites that will slowly pit and wear the spacecraft over millions of years, the rate of this degradation is so gradual that the records themselves are expected to remain largely intact for at least 1 billion years, perhaps longer. 1 billion years is a span of time that resists comprehension. For 1 billion years ago on Earth there were no animals, no plants, not even any multicellular life, only single-celled organisms drifting in ancient seas. And if we project forward 1 billion years from now, Earth itself may be unrecognizable. The sun will be approximately 10% brighter than it is today. The oceans may have boiled away, and whatever descendants of present life still exist will bear no resemblance to the creatures we know. And yet the Voyager spacecraft, or what remains of them, will still be out there, still carrying their golden messages, still orbiting the galactic center, still representing the species that created them, even if that species no longer exists. This makes the Voyagers the most distant artifacts ever created by humanity, a distinction they took from the Pioneer spacecraft, Pioneer 10 and Pioneer 11, which launched a few years earlier and also carry plaques depicting human beings and our location in the galaxy, though the Pioneer plaques are simpler than the Golden Records, containing only images and diagrams rather than sounds and music. And the Pioneer spacecraft are themselves now silent, having lost power years ago, drifting outward on their own slow journeys toward other distant stars. There is also New Horizons, which flew past Pluto in 2015 and continues outward through the Kuiper Belt. And while New Horizons is faster than the Pioneers, it is slower than the Voyagers, and it carries no formal message for extraterrestrial finders. Only a small capsule containing some of the ashes of Clyde Tombaugh, who discovered Pluto in 1930, and so the Voyagers remain our most eloquent ambassadors, our most intentional messages to the cosmos. The Voyagers have also, in their long years of operation, revealed secrets about the very boundary they crossed, sending back data that allowed scientists to understand, for the first time, the true shape of the heliosphere, that protective bubble of solar wind within which all the planets orbit. And for many years scientists imagined the heliosphere as a comet-like shape, with a long tail streaming behind as the sun moved through interstellar space. But the data from both Voyager 1 and Voyager 2, crossing the boundary at different times and in different directions, suggested something quite different, a shape that researchers described, with characteristic scientific whimsy, as resembling a deflated croissant, rounder and more symmetrical than expected, pushed and pulled by the magnetic fields of interstellar space in ways we had not anticipated. It is worth pausing here to appreciate that these missions have now been operating for more than 47 years, which is quite extraordinary when you consider that they were originally designed for a 5-year mission to Jupiter and Saturn, and the engineers who built them in the 1970s could not have known, could not have dared to hope, that their creations would last 9 times longer than planned, would cross into interstellar space, would still be sending data nearly half a century after launch. And this longevity speaks to both the quality of their work and the gentle environment of deep space, where there is little to damage a spacecraft except time itself. And so we come to the metaphor that seems most fitting for these missions: the image of a message in a bottle cast into an ocean so vast that we cannot see its far shore, cannot know if anyone is there to find our bottle, cannot even be certain that the bottle will survive the journey, and yet we send it anyway, because to not send it would be to accept our isolation without protest, to give in to the cosmic loneliness that is perhaps the most profound aspect of human existence, the recognition that as far as we know, we are alone in an unimaginably large universe, and that even if other civilizations exist, they are so far away that we may never find them, never speak with them, never know for certain that they are there. The Voyagers are our answer to that loneliness, our refusal to accept it entirely, our statement that even if no one is listening, we are still speaking, still singing, still sending our music and our greetings and our images of who we are out into the darkness. And perhaps that is enough. Perhaps the act of reaching out matters more than any response we might receive. And perhaps on some quiet night billions of years from now, when our sun has swelled into a red giant and consumed the inner planets and finally contracted into a white dwarf cooling slowly toward absolute zero, the Voyager spacecraft will still be out there, still carrying Beethoven and Chuck Berry and the sounds of Earth, still representing the species that dared to imagine that someone, somewhere, might want to know about us. These are the Voyager missions, the most distant objects ever made by human hands. And now as you rest here in the warmth and safety of your bed, you might picture them out there in the endless dark, so far away that their signals take nearly a day to reach us, traveling through the void at 11 miles every second, carrying their golden records into the future. And you might find some comfort in the knowledge that while we sleep, they journey on, steady and patient and unimaginably far from home, our permanent ambassadors to the galaxy, our message in a bottle to eternity. And the night around them is very dark, and very quiet, and very peaceful. And perhaps that is a good thought to carry with you as you drift off to sleep yourself, knowing that somewhere out there, past Neptune, past Pluto, past the Kuiper Belt, past the heliopause, our little spacecraft continue their long and gentle voyage among the stars.